Hello everyone and welcome. My name is Tanishq Chaudhary and this is the start of a course on stacks. Now stacks are one of the most important fundamental data structures that are asked in interviews. In fact, in an interview setting, you're expected to be well versed with this data structure by default. Unlike most videos on YouTube, this is going to be a very practical course because we're going to look at 15 different interview problems. All of them are popular interview questions from both LeetCode and InterviewBit. In fact, these 15 questions are arranged in such a manner that we go from the easy ones all the way to the harder ones. And I promise you, by the end of the time when we reach the harder ones, even they will feel just as easy. Now I have to be clear, this is not going to be a theoretical course because I'm only going to cover the very essential theory needed to solve the problems. In fact, our focus will more be on things like the way problem statements are framed and the patterns inside of the problem statements that help us figure out that the question is actually a stack-related question. And then we'll talk about the observations and logic needed to commonly optimize these stack-related problems. Finally, we'll move on to template codes, which are going to help us implement all of these much faster. I'm going to cover the 15 essential stack questions along with many bonus videos along the way. And of course, as usual on this channel, all of these video solutions are going to be high quality visual explanations to help you understand and remember better. Anyways, my name is Tanishq Chaudhary and I'm very excited to bring you this course on stacks. So let's go ahead and get started. Hello everyone and welcome. Let's talk about the implementation of stack. We are going to start off with a couple of examples to understand the reason why stacks are built in first place. Then we'll look at the implementation level details of stacks in terms of Python and C++. Alright, let's get started. Now, if I ask you the question, what do you see on the screen? You might reply that there looks to be a couple of books present on a shelf. So you can call this a stack of books. Now, what would you do if you had to read the first book, the book on the top of the stack? Well, you want to read Harry Potter, so you will just pull it out of the stack. You'll remove it from the stack. You'll read it, and then you'll push it back onto the stack once again. Now, this is simple and fine, but what if you want to read Grokking the Coding Interview now? What do? Of course, you can try pulling it out from the middle, but all of these books are dense and heavy, and you don't really want to disturb the balance of the elements on the top of the stack. So what you can do is, you can take out the first book, you can take out the second one, and then finally read Grokking the Coding Interview. You read it, and then you can put it back on the stack, along with these two books. What we have just seen is a very important property of stacks. That is called the LIFO ordering. LIFO stands for last in, first out, saying that the elements that come into the stack towards the end, that is, the elements that come in the last, are the first ones to get out. Last in, first out. Now, this is a property that will exploit again and again throughout this entire series. It's going to be a central property and it's the heart of the reason why we use a stack in many of these questions. Now let's go ahead and formalize the operations we can do on the stack, because we know that if the LIFO ordering is being followed, we have to use a stack. But how do we exactly use it? Well, let's look at a couple of operations. The first operation we saw was removing items from the top of the stack. We call this operation formally the pop operation because we are popping the elements out from the top of the stack, right? So this is going to be the pop operation. The second operation we saw was to add the book back onto the stack. In other words, we're looking at a push operation. Push is the formal term used to define, saying that we want to add an element onto the stack. In other words, we'll push an element on the stack. Now there's a final operation that we do very commonly, and that's the peek operation. Now the peek operation simply says, hey, go ahead and take a look at the top of the stack. Go ahead and take a peek at the top of the stack. All right. So these are three operations that we'll keep in mind. All right. So now let's go ahead and actually look at how these are implemented in terms of Python and C++. Java implementations are pretty close to both of them. So even if you understand just one implementation way, you'll be able to do it in any other language. I have ensured and tried my best to make sure all of the codes are language agnostic. They can be easily translated from one language to the other without having a lot of issues. All right, so let's go ahead and actually look at how we're implementing these. The first thing is, how do we initialize the stack? And in Python, we're going to use the list implementation of stack because there is no inbuilt internal class for it. We're going to create a list, empty list of our own to initialize the stack. In C++ there is, so we're going to use stack, and we're going to have a stack of int variables and we'll call it s. Pretty simple. All right, how do we push? In Python, we do stack.append, and so we can do stack.append an item, and this is going to return a none value. That is, it does not return anything. We just append this element onto the top of the stack. In C++, we simply do s.push. This is going to return a null. All right, how do we peek? How do we check what is the element at the top of the stack? Well, in Python, the way to do that is to use stack of -1. That is, it is going to give you the last element on the top of the stack. Right, so in this case, it's the element 3. How do we do it in C++? We simply do s.top. Now remember, this is a slight terminology difference, but nothing much. You want to look at the top of the stack, you want to peek at the top of the stack, this is how you do it. All right, how about pop? In Python, you do directly stack.pop, and that is going to return your value 3. This is a crucial difference, by the way. In Python, you're going to get a return value of 3. However, in C++, when you do the pop operation, you're not going to get any return value. All right, this is super important, especially when it comes to implementation. Keep the language specific details in your mind. All right, the last thing which we'll also very commonly use is to check whether the stack exists or not. In other words, is the stack empty or not? So in Python, we can simply use the stack variable, and that internally checks its length. So in our case, we appended one element, we checked the top of the stack, and then we popped it out. So the stack is currently empty in both the cases. Now, if you just use stack, if you say if stack colon blah, 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 that is going to return a value of false because the stack is empty, right? In C++, we can do s.empty, which is a function that is going to work on the stack variable, and it's going to return true, saying that, you know what, the stack is indeed empty. So again, small implementation level details that you have to keep in mind. All right, so now that we have a better understanding of how do we implement stacks, let's go ahead and take a look at a real life test case where stacks will be very helpful to understand. Hello everyone and welcome back. In the previous video, we talked about how to implement stacks in terms of C++ and Python. In this video, we're going to take an example problem, simplify path, to build up our understanding of stacks further. In fact, this question is present on both LeetCode and InterviewBit and has been asked in companies' coding interview rounds many times. This in fact forms a basis for a very important point, that how stacks are being used in the real world as well. All right, let's go ahead and get started with the formal problem discussion. So we're given a path, and this path is a Unix path given to us, and the goal of this problem is to return the canonical path. Now, if you're not familiar with how paths or Unix-based paths work, I'm going to link to resources down below so you can check them out first. Anyways, we're given a path and we have to follow 4 conditions to return a canonical path. First, we have to start from a single slash. This slash represents nothing but the root directory. Second, any 2 directories are separated by a single slash. So we can have directory 1 slash directory 2 slash blah blah blah. Condition 3 says that we should not end with a trailing slash. In other words, the slash at the end of it, if there is a slash at the end of it, you have to return it. All right, fourth condition, which is the most important one. It says that it only contains the directories on the path from the root to the target. That is, there is no period or double period directories. Now, period and double period have special meanings. Period basically says that wherever you are, stay. That is, whatever directory you are on currently, just stay over there. Double period means take a step back, right? So whatever directory you are on, take a step back. All right, let's try to formally build up our intuitions and our logic. All right, let's take a couple of examples to understand this better. First things, we have a slash home slash as the input. The blue is the input and the green is the output, which by the way is a common coloring scheme I've followed throughout the rest of this series, so you don't have to worry about anything. All right, so we have slash home slash, and what is the output? The output is slash home. That's because we have a trailing slash at the end of the input, which we remove. All right, let's go ahead and take another example. In this case, we have slash dot dot slash. What it means is we start from the root directory and we have to take a step back, because dot dot really means that you have to take a step back from the current directory. And then we have a slash at the end. So of course you can remove the slash at the end because it's a trailing slash. But now this double dot means that from the root directory, we have to take a step back. But there is no step backs from the root directory. The root directory is where you start. So in fact, this will simply be reduced to staying on the root directory. That is, from the root, if you want to take a step back, you'll end up at the same root. All right, let's take another example. And this time we have slash home slash slash 1337 slash dot slash. First things first, remove the trailing slash. Now what? We notice that between home and 1337, there are actually two slashes. What does that mean? Well, in our case, the implementation level detail is that if there are multiple consecutive slashes, all of them will be useless basically, and we only have to consider one slash. In other words, multiple slashes will get compressed to a single slash. So we have slash home slash 1337. Note that the period at the end now means that we have to stay at the current directory. So we were at 1337 and we stayed at 1337. Let's take a look at one final example, which is going to be the most important one. And this has sort of all of the conditions mentioned in the question. So let's go ahead and formally try to break this down to get the logic. First things first, we start off with a single slash, which is going to be a root directory. This is by default present in all the test cases. We have to start from the root directory. Now what's the next step? We want to go to the next value, which we see is home. Now what does home mean? Home means that we have to go one directory forward. That is, from the root, you have to go to home. All right, so pretty simple. But now you get a dot dot. What does this mean? This means that you have to take a step back, which means that from the root, you first went to home, but now you have to take a step back and go back to the root. All right, pretty simple again. What next? We get a dot dot once again. And since we are already at the root, taking another dot dot simply means that go stay at the root. All right, so now we get a slash tmp. And what does that mean? That means that now we have to take a step forward. We have gotten the directory. And so we'll go to slash tmp. And then we have a bunch of slashes together, that we have two slashes that just gets compressed to one single slash. And then we have a dot. Now dot simply means that wherever you are, stay. So we were at the slash temp directory and we'll stay over there. And of course, the last slash at the end is just a trailing one, so we'll remove it. In other words, the final answer we get is slash tmp, as we saw in the first line of this slide. So now let's go ahead and formally talk about how did we do this? How are we going to implement this going forward and going backward thing? If you have guessed it, yes, you are right. We have to use the data structure stack. Of course, this is a playlist about stack. We have to use a stack. But why do we use it? Again, whenever we have a directory like home or slash tmp, we have to take a step forward. And whenever we have dot dots, we have to take a step backwards. And a good way to simulate that is by using a stack. All right, let me go ahead and show you how this formally works out. So the first thing we get is home. So home means that we have to move forward, which means that we will push the value home onto the stack. That is, we'll append this value to the top of the stack. Now we get a dot dot next. What does that mean? That means that we have to go back one directory. In other words, we have to pop the element out of the stack. All right, we get a dot dot once again, but the stack is already empty. What do? This is a special condition, and we have to say that, you know what? If the stack is empty, you can't really pop anything, and we don't really have to pop either. We were at the root and will stay at the root. So the stack remains as is. Then we have tmp. So what do we do next? This is a directory. So we append it. We push this value on the top of the stack. Now we get a dot. What does that mean? That means whatever directory you are at, stay there. In other words, the stack remains unchanged. So if we have to formalize, what can we say? Let's focus on the core parts. First things first, how do we start? The way we start is at the root, and that is nothing but the Q to initialize the stack, right? Whenever we start, we're going to initialize the stack. Now directory means taking a step forward. What does that mean? That means that we're going to append an element onto the top of the stack. In other words, we are going to push this directory on the stack, right? And what does dot dot mean? Dot dot now means that we have to pop. We have to go one directory backward. So whatever you appended, just pop it back again. And then finally, we have a dot, which means that we really do nothing, do no operations. And this is really it. This is it for the logic of this problem. Let's go ahead and look at the optimized solution, and we're going to code it up from scratch. All right, let's go ahead and look at how do we implement this question in terms of Python code. The first thing we'll do is initialize the stack to be an empty stack, and then we'll start to iterate over the directories in the path. Now, obviously, the path given to us is going to be a string, which is separated by these slashes. So each of them directories, that is any two directories, are separated by a single slash. So we have to say, go ahead and do path.split by the slash. That is, get me the individual directories and we'll see what to do next. So what's the first condition we saw? Remember from the code, remember from the logic. The first condition we can say is that, you know what? If you get a dot, that is, if you get the operation where the directory we have to move to is a dot, that means that we don't really do anything, right? We don't really do any operation on the stack if we get a single dot. Right, what's the other case? Well, if the directory is what? If it's a double dot, what do? If it's a double dot, we have to do an operation called pop. That is, we have to go back one step. We have to pop the element from the top of the stack. So we'll do stack.pop. But now is a very important edge case, right? This is a very important condition I'm going to write. See, it's not always the case that you can pop this directory from the stack. That is, for stack.pop to work, you have to ensure that stack is not empty. Because if the stack is empty and you pop an element out of the stack, that is going to give you an error. Whether it be Python or C++ or Java, all of these languages are going to give you an error if you pop an element out of the empty stack. So first we'll go ahead and check, hey, you know what? If the stack exists, only then go ahead and do the stack.pop operation. What do we do else? What do we do otherwise? Well, in case the stack is already empty and we get a double dot, what does that mean? On an empty stack, which means that we are at the root, and we get a double dot, which means that from the root we have to move a step back, which means that we just have to stay at the root. So the stack remains as is, and this condition, in the else condition, we don't really have to do anything. All right, what's the final case? What the final case is, say that go ahead and append this value to the stack, append this directory to the stack. All right. So this is it, right? We're going to return what? Well, one of the conditions, the first condition in the question says that the path starts with a single slash. So we're going to go ahead and start with a single slash. And since we have all the directories in the stack, let's go ahead and do the join operation. So we'll do join.stack. So what this is going to do is iterate over all the elements in the stack and join them with a slash in the middle. All right. So before we go ahead and run this code, by the way, there's one more condition that is important to know. See, because directories can have a case where we have, say, double slashes, that is, we have slash home slash slash foo slash, these double slashes are going to give us an issue. Because when we split this path by slash, it means that there is going to be a case where there is one slash and then there's an empty string and then another slash. In other words, what I'm saying is we have to add one more condition saying that if the directory is actually empty, that is, if there were multiple consecutive slashes, then we don't have to do anything either. Right? If we get multiple slashes, we just look at it as one slash and we don't really do anything. All right. So this is it for the logic of the code. And let's go ahead and test this out on a bunch of input test cases. Looks to be correct. So let's go ahead and submit this. And we get it accepted. All right, so this is it for the solution to the problem, simplify path. Hello everyone and welcome back. Let's talk about the problem min stack on InterviewBit. All right, so the goal of this problem is to design a stack that supports a bunch of operations. First operation, push. We have to push an element X onto the stack. Very simple. Second operation, we have to design an operation that returns us the top of the element. That is, it is going to see what is at the top of the stack and return it. Third operation, we have to design a function that pops the value out of the stack. We have to remove the top element and return it, right? So all of these three operations up till now are something we've already seen that are like very basics of what a stack is. But now there is a fourth operation given to us, getMin. This function is going to return a value X, which is going to be the minimum value of the entire stack. Now, the only constraint that is given to us is that all of the queries should run in constant time. That is, they should take order of 1 time each. Now, how do we start to think about a solution? Well, since the problem is about using a stack, let's go ahead and create a stack. And we'll start to see what do we do once we get the queries. All right, so this is the simulation we'll run. Let's say we get the query to push the value 7 onto the stack. So now this is how the stack is going to look with the value 7 on top of it. If we get push 3, we'll just add 3 to the top of the stack. We get push 9, we add 9 to the top of the stack. Now let's go ahead and say that we get the query getMin. What do we do at this point of time? GetMin query says that go ahead and get the minimum element of the entire stack, which means that a naive way to proceed about it is to go over all of the elements inside of the stack one by one and find the minimum value. In this case, we find that 3 is the minimum value, so we'll go ahead and return 3. Now, let's say that we get another operation called pop, so we'll go ahead and pop the element out of the top of the stack. Then let's say we get getMin again. Again, what are we going to do? Iterate over the entire stack, go over all of the elements one by one and return 3. We realize that 3 is the minimum value, right? So let's go ahead and say we get another value, another operation, push 1. So we add 1 to the top of the stack. GetMin says, well, get me the minimum value of all the elements in the stack, which means that the value will be 1. Now, if you realize what we have been doing up till now is all of the operations like push and the pop, even the top, are going to take order of 1 time to run, as it does in normal stack. However, the getMin operation is kind of a pain. That is because we have to iterate over the entire stack one by one, taking order of n time, where n is the number of elements in the stack. This means that there has to be a better way to do it. We have to figure out a way to answer the getMin query in order of 1 time. All right, so let's go ahead and talk about the optimized solution. This is one of those questions where if you don't know what to do, you really would have no idea on how to proceed. And in these kind of questions, what we're going to do is we're going to create another stack. That's right. We're not just going to have one stack. We are going to have 2 stacks. First is the blue one, which we already saw, which will handle the queries like push and the pop and the top. But we will also have a green stack, which is going to keep a track of the minimum value we have seen up till now. Let me go ahead and show you the simulation once again, and that will make a lot more sense because it's a beautiful way to approach this problem, right? So let's go ahead and say we get the query push 7. We get the request to do push 7. So we'll just add 7 on the top of the stack. Now, this is the stack we're going to append it to. We're going to add it to the blue stack directly. Whatever query we get, we directly apply it to the blue stack. The green stack will simply reflect the changes of the blue one. So since we added 7 to the stack, the minimum value of the stack is now 7. So we'll add 7 to the stack. Now let's say we get a push 3 operation. What do we do? Because this is a blue case, we'll simply add 3 to the top of the stack. But we'll have the 3 reflect changes in the green stack as well. That is, the green stack is now going to store a value that is the minimum of 7 and 3. Because we have 2 elements on the top of the stack, right? So we're going to have minimum of 3 and 7, and so we'll store 3. Now let's say we go ahead and get the value as, let's say we get a push 9 operation. Now the top of the blue stack will have 9, but the top of the green stack will have the value 3. And that is because 3 is the minimum value of 3 and 9, which is going to be the minimum value of the entire stack. All right, so now what do we do? Now if we get a query get min, what do? We'll simply look at the top of the green stack and return that as the answer. We are not going to pop out anything at this point of time, right? As soon as we get a get min query, we are going to peek at the top of the green stack and return that value. Now let's say we get a operations which says go ahead and pop the element out of the stack. So this is going to pop the element 9, and now we have to make the green stack reflect changes of the blue one. Since we removed an element, we will also have to remove the element from the green stack. Now what if we get a get min query once again? If we get a get min query, we'll simply look at the top of the stack. And since the value is 3, we'll return 3. All right. So now let's say we get a push 1 operation. What do? 1 gets directly pushed onto the pushed onto the blue stack, and the green stack is now going to reflect the changes. Green stack is going to have the value, the minimum of 3 and 1. That is, it is going to take the minimum of the previous element on the top of the stack and the one which we got currently. All right. So now if I get min again, what do? Look at the top of the stack and return 1 as the answer. All right. So this is really it for the logic of the code. What we have done is we have figured out a way to implement the solution using 2 stacks. So let's go ahead and initialize, and let's go ahead and create self.stack, and we'll have self.minStack, right? These are the 2 stacks that we initialize. This is the green one and this is the blue one. All right. Now what do we do when we get a push query? The stack that we have, the blue one, is simply going to reflect the changes directly. So we'll say when we get a push operation, self.stack.append x, nothing special. But what do we do about the min stack? Min stack is going to reflect the changes. So I'm going to say self.minstack.append. Well, I want to append the minimum value of the current x. That is, I'm going to take the current value and find the minimum with the min stack top. So we'll go ahead and do the min stack, find the top value and take their minimum. Right? Pretty simple. This is exactly what we discussed before. But now we have to take care about one thing. This is a common thing which we have to take care across all the stack questions. See, what we have tried to do here is that we have to try to access the -1 element on the min stack. That is, I want to find the top element of the min stack. But this will only work. When will it work? This will only work if the self.minStack is not empty. But if it's empty, what do we do? Look, if it's not empty, we'll simply take the min of x and the top of the stack. But if it's an empty stack, let's just go ahead and directly append this element to the min stack. So we'll do self.minstack.append x. All right, this makes sense. So now what do we do when we get the pop operation? Remember, we have to ensure that all of the changes in the stack are reflected in the green one as well. So when we do self.stack.pop, we have to do the pop operation for the min stack as well. Again, one more edge case, one more condition. You can only do pop when? You can only do pop if the stack is not empty. So we'll say if self.stack exists, that is, there are elements inside of the stack, then you can do pop. But if the stack is empty, pop will really do nothing. So we'll just say it's pass, right? Now what do we do when we get top? Again, here we have to return what is the value at the top of the stack. So we'll do self.stack -1. But wait a second, it is not guaranteed that the self of stack of -1 is going to exist. In other words, the stack might be empty. So if self.stack exists, well, then you can go ahead and do this. But what do we do otherwise? The stack is empty and we're asked to return the top element of the stack. Well, look at the condition. Condition in the question mentions something. What should top do on an empty stack? Return -1. So in this case, we are going to return -1, right? What do we do when we get min now? Remember, in the top function, we return the top of the stack, which is the top of the blue stack. But in the get min function, we're going to return the top of the green stack. So we'll say if self.min stacks exist, well, then you can go ahead and return the self.min stacks top. But if it does not, go ahead and return -1. You can see that there's a lot of parallels between getmin and the top. That's because the only thing that changes is the stack. In top, we use the blue stack, and in the green one is used in the getmin function. All right, let's go ahead and test this out quickly. Looks like this is correct. So we'll go ahead and submit this. All right, we get it accepted. And this is it for the solution to the problem, min stack on InterviewBit. All right, that's it. Hello everyone and welcome back. Now this is after our first section on where we discussed the stack related questions, where we built up our understanding of stacks, the implementation level details, along with a couple of example problems to help us understand things better. In this section, we're going to focus on parentheses related questions, which is actually going to be a step up from the previous one and is going to lead us to calculator related questions in the next section. Now, why are we talking about parentheses questions in the stack playlist? You will get the questions answered very soon. What we're going to look at is a bunch of example problems like valid parentheses, longest valid parentheses, redundant braces, and many more. These are commonly asked in interviews, and applying stacks to these problems becomes a crucial part of understanding stacks themselves. All right, now we will go ahead and take a look at an example and we'll try to build up our understanding of parentheses related questions and calculator related questions later on. Because what we're going to understand is the reason why we use stacks inside of these parentheses questions in the first place. All right, so given this expression to you, let me ask you the question. If I give this to you on a paper and I'll give you a pen to solve this, how would you go about solving this kind of expression? The first thing you would want to do is look at the innermost brackets. That is, the innermost brackets contain the value d. So let's go ahead and evaluate that first, right? We want to focus on the innermost first and then slowly zoom out to the outermost. Now, what do we do zoom out to? We would zoom out to b minus d in the next step. And this would then finally lead us to the entire expression. What we have done is nothing but parsing. Now, parsing is a fancy word for what it means is we have to figure out the structure of the input. That is it. Parsing means to figure out how the input is laid out. Now, why do we want to understand the structure of the input? Why is this kind of thinking helpful? Let's take a look at a simple example. We'll take this simple example, and in this case, we have two opening round brackets and two closing round brackets. Now, if I ask you the question, can you tell me what is the corresponding opening bracket to this current closing round bracket? That is, I've highlighted this closing round bracket for you. Can you tell me which of these is the corresponding correct opening bracket? Pretty simple to answer because we already know the way we do this is by taking the bracket that is the closest. We figured that this opening bracket came in the last and was the first one to get resolved. Wait a second. The bracket which came in the last was the first one to get resolved. That is, we're following something of the sort of a LeetCode ordering. That's right. This is the reason why we use stacks in these parentheses questions. Because when to use stack is answered whenever we see a LeetCode ordering, right? So we have seen that we have to use a stack in parentheses questions and in calculator related questions as well. But how exactly do we use it? How do we use stacks in these kind of questions? What we are going to do is we are going to do a left to right parsing. As I explained earlier, parsing is a fancy word. What it simply means is we have to understand the structure of the input. We have to break it down step by step and understand, okay, this is what gets resolved first and this is what gets resolved later on. Now left to right simply means that we're going to iterate from the left to the right. Okay, enough talking. Let me actually show you with an example. So this is the example case we took earlier, and we have initialized an empty stack on this. All right, so what do we do next? Well, here's a rule that you have to keep in mind. Anything that you get, which is an opening bracket, a character like A, B, C, D, or an operator like plus, minus, division, multiplication, anything of that sort you get, you simply append it to the stack. That is, you push everything except close brackets on the top of the stack. Here's what I mean. Say we get this opening round bracket, we do nothing but push this on the top of the stack. Then we get A, push it on top of the stack, then we get plus, open curly bracket, B, minus, open round bracket, D. The only time when we do not append items on a stack is when we get a closing bracket. This is important. This is very important. If we get an opening bracket, a character or an operator, whatever, we directly add it to the stack without thinking, without having second thoughts. But as soon as we get a closing bracket of any kind, we have to start thinking. All right, so I already asked you the question of what this closing bracket actually closes. What is the corresponding opening bracket? And if you see in the stack, we actually have that value with us. We have this opening round bracket on the top, on this stack here. However, that is not the top element. And it might not always be obvious which of these opening brackets am I closing, right? Because currently we have a closing bracket in our hand and we want to figure out, hey, what is the area that I close? What is the area? What is the expression that needs to be resolved first? Because I'm following the leaf ordering again. So what we do is we'll keep on popping these elements off the top of the stack till we see a corresponding opening round bracket. Here's what I mean. As soon as we get this closing round bracket, we'll go ahead and start looking for the opening round bracket. So we'll pop out D because D is not an opening round bracket. And so D is sort of in an intermediate state. We don't really know if D is part of a valid expression or not. So we'll just keep it hold. All right. Now what we get? On the top of the stack, we see that there's an opening round bracket. What does that mean? Currently, look at the yellow marker. We are at a closing round bracket. And on the top of the stack, we have found an opening round bracket. In other words, everything inside of both of these brackets is going to get resolved. Both of these brackets satisfy each other, both of them resolve each other, and everything in the middle of them will get satisfied. So D is actually part of a valid string now, right? The brackets are balanced in a way. All right, so now let's go ahead and look at what happens later on. We'll keep on iterating and we get a closing curly bracket. Now what do we do? Again, this is a closing bracket, so we have to be careful. What do? We look at the value on the top of the stack. This is clearly not an opening curly bracket, so we'll go ahead and remove it, but we'll keep it on hold. Minus may be or may not be a part of a valid string. All right, so we have B now. Again, B is not an opening curly bracket, so we can't care about that. So B and minus are both at an intermediate state. We can't really say anything about them. But what do we get now? We have an opening curly bracket. In other words, we have found the opening for this closing curly bracket, which we are on currently. In other words, what does that mean? That means we have resolved everything in the middle of these two brackets. So you can see somehow that kind of structure is being followed again. We have sort of parsed the input. We're trying to understand how this input is laid out. All right. So now what do we do next? Let's go ahead and keep on iterating. So we get a star. Again, this is not a closing bracket, so we'll just add it directly. We get a C, not a closing bracket, add it directly. And now we get a closing round bracket. What do we do next? What do we do? Think about it. We're going to keep on popping these elements out one by one. We're going to keep on popping them out till we get an opening round bracket. And as soon as we get an opening round bracket, what do we know? We know that everything in the middle of both of these brackets is going to be validated. And this is the way we have figured out how to parse the input. We knew that we had to use a stack because we could see the leaf ordering being followed in the way brackets were opened and closed. And then we figured out how to exactly go about looking at the opening and the closing of brackets by using a left to right parsing. Now, a quick small implementation level detail is how do we implement this? In the previous example I showed you, we were appending these brackets and the pluses and the minuses directly. And you can do that. You can directly add the elements, or you can also add the indices. Now, different questions will require different cases, but in general, if you want one single template, just use indices. And that's because if you append indices to the stack, you will obviously have a mapping to the elements as well. But if you only append elements to the stack, you might forget which index it came from. Anyways, that's a very small level detail, but still important to keep in mind. Just make sure you are consistent with what you're appending to the stack, whether it be elements or indices, right? So what is the conclusion? Let's summarize this once more. We figured out in all the parentheses and the calculated questions, we have to use a stack. Why is that? Because these brackets were following a leaf ordering. Last ones to get in were the first ones to get out. They were the first ones to get resolved. And how did we figure out how do we use it? We know we have to use a stack, and we iterated from the left to the right, and we parsed the input. We figured out the input and the structure of the string that is given to us. And finally, you can either add elements or the indices to the stack. That's upon you. And that's a small detail you can take care of later on as well. All right, so keeping these three rules in mind, let's go ahead and work out a couple of problems to fully get comfortable with parentheses related questions. Hello everyone and welcome back. Let's talk about the problem valid parentheses on LeetCode. This, by the way, is a slight bit modification of the problem balanced parentheses on InterviewBit. If we are able to solve this, you will obviously be able to copy paste the code and get it accepted for balanced parentheses as well. Anyways, this entire solution is based upon the understanding from the previous video, where we talked about the introduction to all parentheses based questions. We figured out how do we use the leaf ordering, how do we go from the left to right and parse the input, and the way we exactly implement stacks. So if you haven't checked that video out, I'll highly recommend you do, because this solution is based entirely on top of that. In fact, it's going to be a very easy version of what we have seen before. All right, let me go ahead and show you and take you step by step throughout this problem. Given a string s containing only brackets, we have opening and closing brackets of the type round, curly, and square. And the goal of this problem is to return true if s is valid and false otherwise. So looking at the example cases, we have the first one returns the output as true because the closing and the opening brackets match and mix and match appropriately. In the second case, however, there is a stray opening curly bracket which never gets closed. In fact, it is trying to close the round bracket which is going to be invalid. So we have to return false in this case. All right, let's go ahead and talk about the intuitions and the observations needed to solve this question a bit more formally. We'll take the same test case and we'll try to build our understanding from this. Now, if we focus on the opening round bracket, we see that it gets closed towards the very end. We get a closing round bracket towards the very end. So both of them resolve each other out. All right. What about the opening and the closing curly brackets? Well, both of them again mix and match well. And this closing bracket is able to close the appropriate opening bracket. That is, the closing curly bracket wants an opening curly bracket to be present before it. And it is. So we can see that this is also a valid case. What about the square brackets? Again, the opening square brackets get closed by the appropriate closing bracket. So this is also valid, which means that everything inside of this test case mixes and matches well. The opening brackets are closed by the appropriate closing brackets. So we return true in this case, right? Let's take another example. And this time we have something more interesting going on, because we have the same number of opening and the closing brackets. That is, for one opening round bracket, we have one closing round bracket. For one opening curly bracket, we have one closing curly bracket. But the ordering in this case is messed up. That's because if you can notice, this closing round bracket is trying to close an opening curly bracket. Obviously, this will never work because this closing round bracket wants to close an opening round bracket. It cannot close an opening curly bracket. So brackets in these cases do not match. And obviously this is contrasted with the case where we have the same number of opening and the closing round in curly brackets, but one of them is invalid and the other is valid. So clearly ordering matters. And if you notice, the input has to follow this LeetCode ordering that we discussed in the previous video as well. That is, the last bracket to get in should be the first one to get out. And that was sort of the intuition behind using a stack. And we also discussed how do we go from the left to the right and parse the input. Let's go ahead and do that in the next step. One more thing, we also discussed that if the brackets open, add them directly. If the brackets close, check what they are closing. That is, if you get any kind of opening bracket, just add it to the stack without thinking twice. But as soon as you get a closing bracket, what do? As soon as you get a closing bracket, you have to check whether it closes the right opening bracket or not. All right, let's go ahead with the simulation. First thing we'll do, keep on iterating from the left to the right. We get the first element as an opening bracket. What do? Add directly, no thinking. Then we iterate forward and we get an opening curly bracket. Again, since this is opening, we'll just add it directly, no thinking twice. But now what do we get? We get a curly closing bracket. Now we have to be careful. We have to be very careful in what we do. Because as soon as we get a closing curly bracket, what do we expect? We expect that it closes an opening curly bracket, because no other case will work out. This closing curly bracket cannot close an opening round bracket or an opening square bracket. It can only close an opening curly bracket. So now, following that LeetCode ordering again, we'll look at the top of the stack. What is the top of the stack? It's an opening curly bracket. So that's great. For this current closing curly bracket, we found an appropriate opening curly bracket. In other words, both of them validate each other and satisfy each other. Pretty nice, right? All right, let's go ahead and continue iterating, and we get an opening round bracket. Since it's opening, we add it directly. But now what happens next? We get a closing square bracket. What does that mean? Well, this closing square bracket comes in and requests that, hey, can you get me an opening square bracket? Because that is who I can satisfy, right? I can mix and match val with the opening square bracket. So we go ahead and look at the top of the stack, and we see that it's an opening round bracket instead. What does this mean? This means that this closing bracket is actually invalid. And so this will invalidate the entire expression. As soon as we get one invalid case, one parentheses messes up. As soon as one guy messes up, the entire string gets cancelled. Think about it that way, right? Now, just another example is what happens if we had a closing round bracket? What would happen in this case? In this case, what would happen is we would be able to mix and match well with the top of the stack. So we can say that, you know what, this closing round bracket will be able to match with the stack top. Both of them resolve each other, and we can move forward with our lives. Again, this is a closing round bracket. We'll check the top of the stack. Is it an appropriate opening bracket? Yes, it is. So let's go ahead and close that, and we're done. Now, what do we see happening at the end? All of these brackets are validated. All of the opening brackets have been closed. And this is the reason why stack is empty. Remember, this is another important condition which you might miss. The stack should be empty at the end. And what it says is that all of the brackets that opened, which we put into the stack, remember, all the opening were put into the stack and all the closing were removing them from the stack. So if at the end the stack is empty, that is a good sign, because we were able to close all the brackets that ever opened. Now, what's another case that could happen? Let's say that we have another curly bracket towards the end. Now, this is the entire string. What would happen? In this case, we would add it to the stack, but this would never get resolved. In other words, it will be left alone, and it would make the entire expression, entire parentheses, invalid, right? So it's very important for us to follow a couple of conditions. Let's go ahead and formalize the logic, and that should make a lot more sense. All right, let's go ahead and talk about the code for the is valid parentheses question. All right, so first things first, we'll go ahead and create a stack which is going to be an empty list. Next, we want to create a mapping from the closing bracket to the opening bracket. That is, for this closing bracket, for a closing curly bracket, I expect an opening curly bracket to be present on the top of the stack. Right? This is something we've discussed already. We have to do the same for opening and closing brackets for all the kind now. All right, cool. So now that we have created the mapping, we can finally go ahead and start to iterate from the left to the right. So we'll go over all the characters in the string given to us. Now, first things we'll check is that if the character is an opening bracket, if it's round, square, or curly opening bracket, then don't think twice. Just append it to the stack, right? Because as soon as we get an opening bracket, we directly add it to the stack without thinking twice. This is something we've already established. Else what do we do? In the else condition, things get more interesting because now I have to say, you know what, check if the mapping of this character, if the mapping of this closing bracket maps to the correct value present on the stack top. That is, for a closing bracket that I have right now, can you check if it maps to the correct value, that is the opening bracket of curly type on the top of the stack? Because if it does, then it's good. Then it's good, right? And we'll say, you know what, since both of them match, both of them resolve each other. So I'm just going to do stack.pop. I'm going to remove this bracket that matched. All right, what do we do in the else condition? What do we say when there's a mismatch? As soon as there's a mismatch, I'm going to return false. I'm going to be merciless. As soon as you guys mismatch, I'm going to return false right away. Okay, there's one more thing that we need to take care of. See, I've tried to access the stack of -1 here. What have we learned up till now? You just cannot access this stack of -1 just whenever you want. You have to ensure if the stack exists. And only when the stack exists, you can do all of these operations. Well, what do you do otherwise? What if the stack does not exist? What if the stack does not exist and you have a closing curly bracket or closing bracket of any kind rather? In that case, that closing bracket is trying to close something that doesn't exist. In other words, we can just return false right away. All right, so at this point, are we done? Can we return true? Not so fast. This is where another mistake can occur. We have to ensure that the stack is empty. We have to ensure that the length of the stack is equal to 0. Why? Because we already saw this example over here. In this case, we reached the end of the iteration and we had one curly bracket remaining in the stack. And this curly bracket was never resolved. It was never popped out of the stack, which means that it still remains unresolved to this date. In other words, this entire expression became invalid just because the stack was not empty. And just to reframe, what does empty stack mean? Empty stack really means that all of the brackets that were input into the stack, all of the opening brackets that were ever inputted into the stack have been closed. All right, cool. So let's go ahead and run this code and this gets accepted. So let's go ahead and submit this once and we get it accepted as well. All right, cool. So this is it for the solution to the problem, valid parentheses. Hello everyone and welcome back. Let's talk about the problem, redundant braces on InterviewBit. Now, just a quick aside, if you haven't watched the video introduction to parentheses question, I'll highly recommend you watch it because we're directly going to use rules and logic that we formed in that video inside of this question because we're going to apply things directly without talking about it much. That's going to make the solution a lot simpler. All right, anyways, let's talk about the problem statement first. We're given a string A containing operators, round braces, and letters. So we have a bunch of operators like plus, minus, multiplication, divide. Then we have a round braces. So we have the opening and closing round brackets and a bunch of letters. The goal of this problem is to return 1 if A has redundant braces and 0 otherwise. All right, so let's go ahead and take a look at some examples. How do they find redundant? In the first case, we have a redundant brace because we have two sets of round brackets wrapping the A plus B when we only ever need one. In the second case, we see that there are no redundant brackets because we're going to make use of every single one of them. So let's go ahead and take a look at some observations and logic from the test cases given. And really, there is just one single observation that we need to pull out from these. What is that? Let's try to build up to it. The first test case we see is a plus b wrapped in these two sets of braces. Why is there redundancy in this? Because instead of two, we can just use one, right? Let's take a look at the last test case. Here we have a simple letter A, which is wrapped inside of these parentheses, but it looks like we don't really need this. The example and the problem setter says that, you know what, this is a case of redundant braces because you don't really need to wrap A in anything else. And in the middle, we see that we have A plus B. In this case, there are no redundant braces. We're using every single thing. Now, what do you notice? There's actually one thing in common with all of them which makes the solution work. And this is the central observation of the entire problem. What is the observation? The observation is there should be no operators in between these braces. So in the first one, you see between the first set of braces and the second set of braces, there are either no letters and no operators, right? There are no letters or operators. In the second one, there are both letters and operators. And in the third one, there is a letter, but there is not an operator, right? So we have to ensure that there are no operators between any two sets of braces. Because if we can make this condition work, then we'll have a case of redundant braces. All right, just a quick aside, what are some of the rules that we saw earlier? Rules, when did we decide when we have to use a stack? We use a stack whenever we see a leaf ordering being followed. And that is true for all parentheses questions. So in this question, we're also going to use a stack. How are we going to use it? We're going to go from the left to the right and parse the input. See what structure this input is following. And finally, how do we implement this? In this question, the elements are the bigger focus instead of the indices. So let's just focus on elements. Let me actually go ahead and show this to you. Right. As we discussed, there should be no operators between any two sets of braces. This is something we'll keep in mind as we go through the example. All right, so let's go ahead and iterate from the left to the right one by one. So let's say we have the first element and that's the opening bracket. So let's just push it onto the stack. Again, if we get an opening bracket, if we get an operator, or if we get a letter, we push that onto the stack. The only time we don't push an element onto the stack is when we get a closing bracket, because then we need to be more careful. Again, this is something I've already explained in the parentheses questions, the introduction to parentheses questions video. If you haven't checked it out, if you haven't understood it well enough, go ahead and dive into it once more. Right. Cool. So we'll go ahead and continue iterating. We get another opening round bracket. So we'll just add it to the stack. Now we get A, then we get plus, and then we get B. Nothing special. These are just opening brackets, operators, or letters. We add them directly onto the stack without any question. Only when we get a closing bracket, then we have to be careful. All right, so now that we have gotten a closing bracket, let's try to be more careful with what we do. What's the first thing we do? Well, this closing round bracket is looking for an opening round bracket to close. Makes sense? So we look at the stack top. Well, that's an element B. B is not really useful for us. So let's just go ahead and pop that and we'll keep it as an intermediate state. We don't really know if B is useful or not. And then we see a plus. Now, what does that mean? Look at the condition on the top right. The question wants that there should be no operators if you want to have a redundant brace. That is, if you can find an operator, in this case, we have found an operator. That means that the expression that we're going to enwrap in these two opening and the closing round brackets is actually going to be a non-redundant one. We need those braces in this case. Again, that is just how the problem is defined. So now since we have found an operator, let's go ahead and keep that in mind. And we'll keep on popping these elements out one by one again. So we pop out plus, and then we also pop out A. But now what do we have? On the stack top, there is an opening round bracket. And what do we have currently? The pointer is pointing to a closing round bracket, which means that everything inside of this has to be considered together, right? Now, since we found an operator, what can we say about this current highlighted section? We can say that this is actually a non-redundant case. So this is actually a valid case of how braces are being used. So let's not touch this. We'll just keep on iterating forward. So now we get a plus. Again, it is not a closing bracket, so we can just add it directly. No thinking. Again, opening bracket, good to go. C, good to go. But now we have a closing bracket. So let's try to be more careful this time. Now what do? The first thing we do is look at the stack top. We have an element C. Again, it's not an opening bracket, so let's just pop it out, keep it as an intermediate state. And now what do we have? We have an opening bracket. So we have found an opening bracket for this current closing bracket. What does that mean? That means that the entire highlighted expression is what we have to look at right now. But look at this. There was no operator that we found in the middle, right? There was no operator in this highlighted expression, which means that there are redundant braces. And that's correct. So this is what it means. We have found a redundant bracket and we can return true that yes, indeed, there are redundant brackets in this input. All right, so let's go ahead and take a look at the optimized solution and we'll go ahead and code this up. All right, so this is going to be the code where we start from an empty stack. Again, very simple. And then we'll go ahead and iterate over all the characters in the input string, right? Now, as I mentioned, what is the first condition? The first condition is if you get a letter, if you get an operator or an opening bracket, that is, if you get anything other than a closing bracket, just directly append it to the stack. No thinking at all. All right. When it goes to the else condition, we have to be a bit more careful. So in the else condition, what we'll do is we'll keep a track of the count. And this count keeps a track of a count of the number of operators we have seen. Because remember, that is what is going to tell us whether a bracket or whether an expression inside of the input is redundant or not. So we'll start the count from 0 and we'll say, you know what, since we have found this closing round bracket, let's just go ahead and keep on popping these elements out from the top of the stack one by one till we get a opening round bracket, right? Till we get a opening round bracket. So we'll go ahead and say now if the popped is actually an operator, that is, if it's any of the plus, minus, star or division, if the character is any of these operators, then I want you to do count plus 1. In other words, since we have found a positive number of counts of the operators, whatever the expression is going to be a valid non-redundant expression. And of course, at the end of this while loop, we're going to do a stack.pop because we want to pop out this opening bracket. We don't really have any use for this at all. Anyways, now what do we do? Once we're done with this entire iteration of this while loop, we're gonna check what the condition is. We're gonna say if the count is 0, that is if the count did not change at all. In other words, we did not encounter any operators. If we did not encounter any operators, return 1. We have found a case of redundancy. And if not, we'll just keep on going forward again and again and again. And if throughout the entire iteration of this entire string, you find no such redundancy, then you can safely return 0. That is, the entire string is non-redundant, right? So let's go ahead and test this out. It looks like it works. And we'll go ahead and submit this as well. Cool, so this gets accepted and this is it for the solution to the problem, redundant braces. Hello everyone and welcome back. Let's talk about the problem minimum remove to make valid parentheses. This, by the way, is a medium level question on LeetCode and we're going to use this problem to build up our solution for longest valid parentheses as well. In fact, this solution is going to convert that hard problem into an easy one. I'm not even kidding. All right, let's go ahead and get started with the problem statement. So we're given a string that contains opening and the closing round brackets and lowercase English letters. The goal of this problem is to remove the minimum number of parentheses to make S valid. So in the first case, we see that there are 2 opening brackets and 1 closing bracket. And we see that we have to remove any one of these opening brackets to balance these opening and the closing ones out. Okay, pretty simple. And so what I've decided to do is I've decided to remove the first opening bracket and keep the second one. You can also do it the other way. Both of them are perfectly fine. In the second case, we have the input as 1337 wrapped inside of brackets. In this case, I have to remove no such parentheses to convert it to a valid string because it's already a valid string. All right. So let's go ahead and take a look at some observations and logic to build up to the solution. Now we already talked about this test case where we remove the first bracket. But I want you to notice one more thing. The question clearly mentioned that we can only remove brackets. That is, we have to remove the minimum number of brackets to make it a valid string. In other words, We're only going to remove brackets and never the lowercase English letters. Now this is important because what we can do is simplify our life a bit. What we can do is look at these characters instead as indices, and we can filter out all of those characters which are lowercase English letters. In this way, we have simplified the problem quite a lot, and now we only have to worry about the brackets opening and closing. All right, so let's go ahead and talk about a couple of rules that we discussed previously. First was the thing where why do we use a stack and when do we use a stack? As soon as we see a leaf ordering being followed, we are going to use a stack. And in this question, it's a parentheses question, so we will use a stack. The second thing was how do we use it? Well, we're going to go from the left to the right and parse the input. That is, for every opening bracket we see, we'll go ahead and add it to the stack. And for every closing one, we're going to remove an opening from the stack. So both of them are going to resolve each other. This will make sense in a second, don't worry about it. And the third one is how do we implement this? In this case, it is better to use indices instead of elements. Okay, because we did a filtering out operation, which means that indices are going to be the way to go. All right, so let's go ahead and get that input set up. And now we have an empty stack with us. So what we'll do is we'll go ahead and start to iterate from the left to the right. So first we'll go ahead and look at the element 0. All right, so element at the index 0 is an opening bracket. So we're going to add it directly onto the stack. No questions asked. Then we move on and we iterate further and we find another opening bracket at the index 4. So we'll again add the index 4 to the stack. Oh, by the way, I'm adding these indices and you have to focus on getting these indices into the stack. The brackets are there just for the sake of demonstration and understanding. We're actually going to only have indices in the stack, not the brackets. Anyways, then we go ahead and we iterate further and we find that we get a closing round bracket. Now, what does this mean? We have found a closing round bracket, which means that it is going to satisfy the opening round bracket. So this 9 is going to get satisfied with the 4. Both of them mix and match together and will pop the element 4 out of the stack. This is the reason why you see 4 and 9 in the answer. Make sense? Now we reached the end of the iteration, but 0 still remains on the top of the stack. In other words, it never gets satisfied. It never finds any closing bracket to resolve it. So we'll leave 0 out. So the minimum remove to make valid parentheses is going to remove the element 0 from the input. Okay, let's go ahead and take a look at another example, and this one will really bring forward the core of the problem. So let's go ahead and start iterating from the first element. We see 0, which is a closing bracket. Now this closing bracket is going to close an opening bracket. But do we have an opening bracket on top of the stack? Well, no, we don't even have any brackets on top of the stack. We don't have any brackets at all, which means that this closing bracket will never get satisfied. It will be alone always and forever. So we're going to leave it and we're going to iterate further. All right, so now we get an opening bracket. Let's go ahead and add it to the stack. Pretty simple. Next iteration, we see that we get a 4. Now this 4 did what? As soon as this 4 got an opening bracket, it popped it out and satisfied both of them. So now both the opening and the closing brackets have satisfied each other, which means both of them are essential to be a part of the solution, right? So let's go ahead and continue iterating. Now we get 6 and this is an opening bracket. So let's just go ahead and add it to the stack. Then we get a 7, also added to the stack. And then we get a 9. What do we do when we get a 9? That's right, we'll pop out the 7 and now both 7 and 9 will satisfy each other. At this point, we have 1, 4, 7 and 9, which are the parentheses which satisfy each other. In other words, they form an essential part of the answer. However, 0 and 6 have to be removed, right? We had to remove a minimum number of brackets, and this way we have found 2 brackets to remove from the answer. Okay, pretty simple. But what would happen, say if I get 10, which is a closing bracket, just for thought process sake. As soon as I get this 10, what would happen? This 10 is going to satisfy the element on the top of the stack, which is the element 6. So 10 and 6 are going to satisfy each other, and so there is where we end the iteration. All right, let's go ahead and take a look at the optimized solution and okay, cool. Let's go ahead and get started. Now, if you notice, what we have done up till now is have a differentiation between these blue and the green ones, right? The blue ones were ones that never got satisfied and the green ones were the ones which got satisfied. So the first thing I'm going to do is create an array called isOK, which is going to be initialized with 0 for all the values of the string. In other words, I'm going to say none of the elements in the original string ever get satisfied. That is my initial assumption, and I'm going to build upon that later on. Now I'll also have an initial stack, and we'll go ahead and start iterating over all the elements inside of the string. So we'll first get its index and then the character for every single element of the string. Now if the character is an opening bracket, what do we do? If the character is an opening bracket, we add it to the stack without asking any questions. Now, what happens when we have a closing bracket? When we have a closing bracket, we'll first ask the question, hey, does the stack exist? Is there any opening bracket on the top of the stack? Because if there is, what do we do? If there is, we will pop that element from the top of the stack and assign its index the value 1, saying that this opening bracket which we just popped out is actually a 1. It is okay. It is a green value. As we saw in the case for 1 and 7, both of them were opening brackets and they got satisfied by 4 and 9 respectively. So 1 and 7 both get this 1. And we also assign isOK of I to 1 as well, saying that because 4 was the one that popped out 1 from the top of the stack, 1 gets satisfied, but also 4 gets satisfied. So we're going to satisfy both of them. And what is the else condition? What if the stack is non-existent? What if we get a closing bracket and then we realize that, hey, wait a second, the stack is empty. So we can't really close any opening bracket. In other words, we'll just have to continue, unfortunately, skipping over this current I. All right, so what's the final else condition? If we get an opening bracket, we append it to the stack. If we get a closing one, we check the stack for emptiness or not and figure out what to resolve. But there's a final condition which says, if you have English letters, well, go ahead and also continue because we don't want to mess with any lowercase English letters. What we are only going to mess with the indices of the parentheses. All right, so at the end of this iteration, isOK is the array which contains all the information. It is the one which contains the information of which all are blue, which all are 0, and which all are green. The green represents 1 and blue represents 0, right? So let's go ahead and iterate further. Now the goal of this problem is to return the string. We have to return the string by removing the minimum number of parentheses. Now using this isOK array, we've already found out all the parentheses which are essential and which are non-essential. So what we're going to do is we're going to go ahead and build the answer character by character once again. Remember, all of this, what this stack did was to store the indices of the elements. And this is why the isOK thing worked out. Now we're going to iterate over the string once again. And we're going to ask the question, hey, is the character a bracket or not? Because if it is a bracket, and only if it is okay, only if it has been satisfied, then we add it to the answer. Because if it's a bracket and it has not been satisfied, we'll have to continue. We'll have to pass over this test case. Now what's the else condition over here? If the character is a bracket, then you'll have to check if it's okay or not. But if a character is not a bracket, that is, it's a lowercase English letter, then by default, you have to add it to the answer. All right. Anyways, at the final point of time, you go ahead and just return the answer. So let's go ahead and run the code for sample test cases and submit this. All right, cool. So this is it for the solution to the problem, minimum remove to make valid parentheses. Hello everyone and welcome back. Let's talk about the problem, longest valid parentheses. Now, if you haven't seen the video on minimum remove to make valid parentheses, this question will seem out of the blue. However, if you have seen that, this question is just a breeze question because we're going to use the exact same logic as we saw in the previous one. All right, let's go ahead and talk about the problem statement formally. And we're given a string of just opening and the closing brackets. That is, we only have opening and the closing round brackets. The goal of this problem is to find the longest substring of valid parentheses. In other words, let's take an example. In the first test case, we have the opening and the closing brackets which form a length of 2, but then we have 3 opening brackets which never get closed. In other words, the longest substring of valid parentheses is just 2. Now the second test case is one where we have opening and closing bracket, and then we have a bunch of opening brackets, but then one opening bracket at the end gets closed. Now what is the longest substring of valid parentheses? We have in this case 2 sets of the length 2 substring of valid parentheses. Since both of them are of length 2, we'll just return 2 as the answer. Now, what can we say right away about this kind of question? This kind of question is actually twofold. We have to find two things first. First, we have to figure out what all parentheses are valid or not. Because once we have the valid parentheses in hand, once we know which of them are valid, which of them are invalid, we simply have to find the longest substring of them, right? So this is going to be broken down into 2 parts. And if you realize, the answer to the first one is something we've already seen. All right, since there is not a lot to go on, let's go ahead and just build up our logic from the previous question. As with the previous one, we'll set up an isOK variable that is going to be all zeros of the length n. In other words, it is going to say that, you know what, I'll assume none of the brackets opening or closing ever get satisfied. All of them are zeros. We'll also have an initialization of the stack, and then we'll start to iterate over all the characters in the string. As before, we'll check if the character is an opening bracket or not, because if it is an opening bracket, we'll just directly add it to the stack. What if it's a closing bracket though? In the else condition, it's a closing bracket, we'll have to check if the stack exists or not. That is, for this current closing bracket, because I've gone in the else case, for this closing bracket, does the stack exist? In other words, is there an opening bracket? Is there any opening bracket that you can find which had been put on the stack? Now, if you can find that is the case, well then go ahead and make both of them satisfied. That is, go ahead and pop the element from the top of the stack, which is going to be an opening bracket, and set its value to 1. That is, that opening bracket has been satisfied by this current closing bracket. And obviously that also means this current closing bracket has been satisfied. So we'll set isOK of I to be 1. In the off chance that the stack is empty and you get a closing bracket, well, that's just sad. We can't really do anything about that. I'm sorry. Anyways, once we're done figuring out which of the brackets opening or closing are valid or not, we simply have to figure out the longest substring of these valid cases. So what we'll do is we'll set up a count, which is going to be a running count of all the values. And we have an answer, which is going to store the maximum of all of these counts. So what we're going to do is we're going to iterate in the range of n. That is, we'll iterate over every single index and we'll ask the question, hey, is the bracket I'm looking at, is the current bracket okay or not? Because if it is okay, well, that's great news. Whatever the count was, increase its value by 1. Why? Because I've found the case of a valid parentheses. Right? So as soon as I know this current bracket is a part of a valid substring, go ahead and add 1 to the count. Else what do we do? If at this point of time there is a bracket which is a stray bracket which never gets opened or never gets closed, well then we unfortunately have to reset the counter from 0. Right? So the next step is then going to be simply taking a max of the answer in the count. Because answer wants to store the maximum possible value of all the counts ever. All right, so this is it for the code. Let's go ahead and run it. And we'll go ahead and submit this as well. And cool, this gets accepted. So yeah, this is it for the solution to the problem, longest valid parentheses. Hello everyone and welcome back. This is the start of a new section on calculator related questions. It builds on top of our previous work on parentheses related questions, where we discuss the exact reasons why we use a stack, how we use it, especially the left to right parsing method, and the implementation level details that we need to take care of. Now what I'm going to do in this video is establish that we just need 2 steps. That's right, just 2 steps we need to know to solve any calculator related question. In fact, both of these steps individually are interview problems on their own, which means that once we solve both of these questions, we'll be able to solve any calculator related question. That is like killing 3 birds with 2 stones. All right. So the first step is to parse the input from the infix to the postfix notation, and the second one is to evaluate the postfix notation. Now the first question that you should ask is, wait, what is the postfix notation? So let's go ahead and talk about the introduction to the postfix notation first. All right, let's go ahead and take a simple example, and let's say that we have this kind of string that we need to evaluate. Now the infix notation is formally defined as such. In the infix notation, the operator is fixed in between the operands. Again, the operator is the focus over here, and the operator is going to be fixed in between in the operands. Now what is the postfix notation? Formally speaking, postfix notation is where the operator is present after the operands. Now that might sound a bit unnatural given that what we have been looking at all throughout our life is the infix notation. This is the simple infix notation over here. And if I ask you the question, hey, how would you go about evaluating this kind of thing? What would you do? The first thing we'll look at is brackets. So we'll evaluate everything inside of the brackets. So 3 times 3 becomes 9. And so this is the expression that we have now. What do we do next? We realize that we have to do a division operation first, which means that we'll do 9 by 7 C-style division. So 9 by 7 will get rounded off to 1. And now we have 0 minus 1 plus 1. And since plus and minus are of the same priority, we'll simply cancel both of them out and say that the final answer is nothing but 0. Now what have we done over here? What we have done is simply apply a rule called BODMAS, which stands for bracket, order, division, multiplication, addition, and subtraction. This is a rule that is commonly taught in high school math and is the way we evaluate any sort of input given to us. However, there is a small catch. See, if you have brackets inside of brackets, those brackets inside of brackets need to be resolved first before you evaluate the brackets. And if you have brackets inside of brackets, then you need to resolve the innermost bracket first, then zoom out and then zoom out once again. You can see that this sort of nesting is what can give rise to such complicated expressions. And while the first one on the top is pretty easy to solve, using the same infix notation, the second one becomes much more harder. And so the question arose whether we can write the expression unambiguously and we can solve it efficiently. That is, without having to worry about this BODMAS rule, is there a way we can write this expression? And secondly, is there an efficient way to solve that expression once you have written it that way? This is the idea behind postfix notation. The postfix notation simply says that the operator is present after the operands. In other words, if we take an example like this, where we have 1, 2 plus, it is equivalent to saying 1 plus 2. Again, I know this sounds unnatural, but bear with me for a second because something interesting is going to happen. Let's say if we have 1, 2 plus 3 star, what will that evaluate to? 1, 2 plus will become 3, and then we have 3, 3 star. In other words, we'll have 3 times 3. What we have done is 1 plus 2 inside of brackets that needs to be resolved first, and then we'll do times 3. Do you notice something? If we go back the other way around, we have figured out a way to write these bracketed expressions into non-bracketed ones. That is 1 plus 2 which had to be resolved first, which were present inside of the brackets. We found a way to write that without using the brackets. How nice is that? We were able to figure out a way to unambiguously write this expression. Alright, so this is the general idea behind using a postfix notation. And so we can finally formally talk about these two steps again. The first step was to convert and parse the input from the infix to the postfix notation, and that is something we're going to look at in the next video. And then in the next one, we'll look at how do you evaluate the postfix notation. Alright, so let's get started. Hello everyone and welcome back. Let's talk about how do we convert the infix to the postfix notation. As we discussed, the infix notation is one in where we put the operator in between the operands. That is, we fix the operator such as a minus between the operands such as 0 and 1. So we have something like 0 minus 1. In the postfix notation, we have the operator after the operands where we have something like 0, 1, minus. Let's go ahead and take a look at some examples to understand this better. In the case we have 1 plus 2 in the infix notation, it gets converted to 1, 2 plus. If we have say 5 minus 6, it gets converted to 5, 6 minus. And then if we have something like 1 plus 2 times 3, we have 1, 2 plus 3 times. Wait a second. 1 plus 2 times 3 will evaluate to 1 plus 6, which is nothing but 7. But if we actually evaluate this, it'll come out to be wrong. That's because 1, 2 plus will get evaluated to 3 first. And then we'll have to do 3 times 3, giving us the answer 9. This is in fact wrong. We are doing 1, 2 plus 3 times, which is wrong. So what do we have to do instead? We have to switch out the ordering of this plus. Because now what we have done is we have done 1, 2, 3 star plus, basically saying go ahead and multiply 2 and 3 first. So 2 times 3 becomes 6, and so we'll write 1, 6 plus. Now 1, 6 plus is what? It's nothing but 1 plus 6, which is 7. And so now we have the correct answer. But if you notice what happened over here, we realize something. The ordering of these plus and the star operators changed. Right? We had 1 plus 2 times 3. And it became 1, 2, 3 star plus. So the ordering of the plus and the star operators changed. Although the ordering of the operands like 1, 2, 3 did not change. There's something interesting which we'll come to very soon again. Alright, so now we want to formally talk about how do we convert the infix notation to the postfix notation, right? So let's go ahead and try to work out the answer one by one. So using the BODMAS rule that we know, we can say that, you know what, let's go ahead and do the division operation first. Alright, so we have to do B by C first, and how are we going to write B by C? We're going to write it as BC slash. Alright, pretty simple up till now. Then what do we do next? We also realize that there's a B by C times D. We have to do times D in the next step, because that is the second operation we have to follow using the BODMAS rule. So how do we write times D? Well, BC by forms one single operand now. And so we have to multiply BC by with D. BC by is one operand and D is another. And so we can write BC by D star. All right, how do we handle the plus case and the minus case then? Well, let's go ahead and handle the plus one first. So we have A plus this entire expression. How can we handle that? We can write A in the front and plus the end. And then we have minus E towards the end. So we can write it as E minus. Right? So we have followed the BODMAS property and we have written down the infix to the postfix notation. In fact, if you break it down, we have something of this sort. First, we looked at BC slash, then D star, then A plus, and then E minus. Following the BODMAS rule exactly. In fact, what we have done here, in other words, is that we have somehow implicitly encoded the information of the BODMAS rule into the postfix notation. Now, to evaluate the postfix notation, we won't need this BODMAS rule at all, because we have already encoded that information in the structuring of the postfix notation. Right? Let me go ahead and explain that further. What we have done is that we looked at the BODMAS rule, and we figured out that we have to first look at brackets, then order, then division and multiplication at the same level, then addition and subtraction at the next lower level. Right? So this is something we've implicitly encoded into the answer. Look at the ordering of the operators. We have slash first, then star, then plus, and then minus. I also want you to notice another thing which I brought up earlier as well. The ordering of the operands, which are A, B, C, D, and E, remain the same from the infix to the postfix notation. Only and only the ordering of the operators change. It went from plus, slash, star, minus, that is, it went from a completely random ordering to a well-defined ordering, where we had division, multiplication, addition, and subtraction. So now the question is, how do we implement this? How do we make this happen using formal logic? What we're going to do is we're going to go ahead and use a stack to do this. Let me actually run a simulation and show you how this works. The first thing we'll do is we'll start to iterate from the left to the right. And so let's say that we get the first element as A. Since this is the operand and we don't mess with the order of the operands, we are just going to write it as a part of the answer directly. No thinking twice. You see an operand, you write it in the answer. That's it. As simple as that. What's the next step? The next step is to iterate further and we see that we get a plus sign. Since the ordering of these operators do change later on, we'll keep them in a stack for now and we'll see what to do later on, right? So now we add this plus to the stack. Then we get the element B, and what do? Since B is an operand, we'll add it and append it at the end of the postfix answer. All right, cool. So now we get a slash. Now I'm going to ask you a very important question. Is it okay to put this slash after this plus? Or should we instead remove this plus first and add the slash later on? What should we do? Let's think about something that is going to happen. If you remember, stack follows something called the leaf ordering. The last one to come in is the first one to get out. And notice what the answer on the top right hand side says. The answer on the top right hand says that we have to have division, then multiplication, then addition and subtraction. That is, we have to follow this highest to lowest ordering in the postfix notation. That is something that we have to encode in by default. Now, if it means that we have to have the highest priority operators first and the lowest ones later on, using this LIFO notation, what should be the ordering we follow in the stack? Again, the last ones to get in will be the first ones to get out. So if we want the highest ones to come first in the answer, we'll have to ensure that the highest ones are the first one to leave out of the stack. In other words, we have to say that the stack follows the lowest to highest ordering. So in fact, what we have right now, plus followed by a slash, is okay. Because in the edge case that we ever decide to remove both of these elements, first we'll pop out slash and then plus, which now exactly follows the ordering we want, right? So I think that should make a lot more sense now. So let's go ahead and continue iterating. We get the element C, and since this is an operand, we'll directly add it to the stack. Now, what do we do when we get a when we get a star operation? Remember the BODMAS rule. It says that first you resolve brackets, then order, then division and multiplication at the same level. What does it mean for us to get a division and a multiplication right now? This is nothing but going to hint us at the fact that this multiplication operator is actually going to take this division operator and kick it out, because both of them are of the same priority. And remember, what is the ordering of the stack? The ordering of the stack goes from the lowest to the highest. All right, we can't allow elements of the same priority to stick in together. So we'll have to kick out the slash, and only then we can add in the star. Again, if you look at it, it is still going to maintain the lowest to the highest ordering now, right? It only happens after we kick out the slash. And if you look on the top right hand side, we can see that, you know what, this is indeed the correct way to go. So we're thinking about this correctly. Anyways, let's keep on iterating further and see what happens. We get a D, and since this is a what? Since this is an operand, we'll add it directly to the answer. Then we get a minus, and now what happens? The priority of minus is much lower than that of multiplication, which means that this minus is going to kick out the multiplication. You can think about it this way. You can think that an undeserving candidate comes, a lower priority element comes, and it kicks out all the higher priority or the equal priority elements out of the stack. It says that, you know what, you guys are much higher priority than me. Minus comes in and says, you know what, addition and multiplication are both either higher or equal to me. So I'll kick you both out. Let me just go and stay in the stack. So we'll go ahead and first kick out the multiplication operator, and then we'll again compare it with the addition one. So now we'll say, okay, you know what, since plus and minus are both of the same priority, let's go ahead and kick out plus as well. Then we'll add minus into the stack. Okay, so now we can go ahead and continue iterating, and we get the value E. We'll just add it to the answer, and then wait a second, we have reached the end of the iteration, right? After E, we have reached the end of the iteration. So what do we want to do? We want to empty out the contents of the stack. And since there is only one single element, let's just go ahead and add this at the end. So now you can go ahead and compare both of them and realize that, you know what, we were actually right. All of this logic worked out for us. So now we want to go ahead and formalize the logic and write it in terms of code. And we're going to follow the exact same things that I taught you before. First things first, let's create a postfix array, which will return at the end. And now we'll also create a stack for the operators. The stack is only ever going to store the operators and not the operands. Now we want to start iterating over every single element in the infix. And we're going to call this element token because it can either be an operator or an operand. We don't know yet. Now we'll ask the question, hey, if the token is not an operator, that is, if it's a letter or if it's a number, a digit, something like that, if the token is not in the operators, then what do? It means that the token is actually an operand. And in that case, we realize that we just have to directly append it to the postfix notation. We don't ask any more questions, and that is it for an operand. Now, what happens if we have an operator though? Then obviously we want to append this item to the stack. We want to push the token onto the stack. Remember, stack follows the lowest to highest ordering, which means that we have to write 1 or 2 lines of code more. And this is very important, and this is something we'll come to, by the way, in the next section as well. Okay, so let me explain what's going on here. I'm going to say while the stack exists, that is while there are elements in the stack, and the priority of the element on the top of the stack is greater than the priority of the current token. That is, we're looking at something like a minus as the current token, and the top of the stack is a star, which we had a case like that before. If we have a case like that, then this current token of lower priority is going to kick out the element from the top of the stack. And it's going to kick that element from the top of the stack. We'll do stack.pop, and whatever the element was kicked out is going to be appended to the postfix one directly. So we are going to say while that is true, while the current priority of the token is lesser than equals to the priority of the element on the top of the stack, then keep on doing this pop operation. Because we are strict, we want to have a lowest to highest ordering. We can't even allow elements of the same priority to be there. Because even if the priority is same, we're still going to make a kick operation. We're going to kick that element out from the top of the stack and append it to the postfix notation. All right, cool. So this should make sense now because we have to follow the lowest to the highest ordering. Okay, what's the last step then? Are we done? If you remember, we had the case where there was one single element minus in the stack remaining at the end. So we'll actually have to handle cases like that as well. And we have to say, you know what, while the stack exists, while there are a bunch of operators in the stack, go ahead and pop that element out of the stack and append it to the postfix. Now, obviously, in this kind of case, we will only ever have one single element like that. Okay, anyways, all of this was to convert this kind of input as we saw on the top from the infix notation to the postfix notation. But now I ask you the question, is it possible to somehow include in brackets as well? Because look at the inputs. We have never talked about brackets up till now. We've only talked about operands and operators. What if there are brackets? All right, let's go ahead and write some more code. And since brackets are of higher priority, since, in BODMAS rule, we always take care of brackets first. Let's go ahead and handle the cases of brackets in the first two conditions. So the first thing we'll say is that if the token is an opening bracket, what do? We will append this token on the top of the stack. We'll say, you know what? This is going to start off a new expression that we need to take care of earlier on. So let's go ahead and append this token on the top of the stack. Okay, now what? Well, we want to say, you know what? If the token is a closing bracket, then we need to do something more. As soon as we get a closing round bracket, what do we want to do? We want to take care of all the elements present between this opening round bracket and the closing round bracket. So what we're going to do is we're going to say, you know what? While the stack top is not an opening bracket, go ahead and kick out all the elements one by one. So what we are going to say is everything in between of these two brackets, between this opening round bracket and the closing round brackets, go ahead and pop those elements from the top of the stack and keep on appending them to the postfix notation. One last thing that we have to do. What is the one last thing? The stack top is currently now having the opening round bracket as the stack top. Why is that? Because that is when the while loop exists. Because the stack top is going to have the opening round bracket, which means that we have to take care of that once again. We have to do a stack.pop operation saying that, you know what, we don't really care about brackets in the postfix notation, because that was the whole point of postfix notation, to get rid of the brackets and the weird BODMAS ordering. Now let me ask you this one question, and this is a kind of a special trick case that we need to take care of. Remember the BODMAS rule, right? And what I promised at the start was that we will be able to somehow implicitly encode the information of the infix notation in the postfix notation, right? And we were able to do that by handling the cases of brackets separately and division, multiplication, addition, subtraction, all right? But now if I ask you, let's go ahead and also formally define the priority. What is that going to look like? Because we use this priority over here in the while loop, right? Now, how do we define the priority? Well, the priority will be a little bit different. So obviously the order has the highest priority, then division, multiplication, and then addition, subtraction. But the bracket, the opening bracket, will have the lowest priority. Why is that, you ask? It has a very interesting reason behind it. All right, let's say that we have a bunch of elements in the stack. Let's say there's an opening bracket, and now let's say that the operator is simply a star. So we have an opening bracket and a star after it. Now let's say that the minus comes, right? So what is minus going to do? Minus is a lower priority element, so it is going to kick out the star out of the stack. But at the same time, we want to ensure that this minus does not kick out the opening round bracket, because it's not minus's job to handle that. It's the job of the closing bracket to handle that in its own while condition. So we are going to have opening bracket having the lowest priority, so that the minus or any other sign, in fact, is never able to kick it out of the stack. All right, so in this video, we learned how to convert the infix notation to the postfix notation. Now, I promise you in the next one, we're going to look at how do we evaluate the postfix notation, and that is going to be so much simpler than this code. Hello everyone and welcome back. Let's talk about how to evaluate the postfix notation. In the previous video, we looked at how do we convert the infix notation to the postfix notation. And I promised early on that the postfix notation is going to be a very easily computable way to get the answer for any calculator related question. What we're going to do is very simple. We're going to create a stack, and now we'll see that we're going to start iterating from the left to the right. Now, for elements like 0, which we'll get as operands, we're going to push them onto the stack without asking any questions. As soon as we get another operand, let's say in the case of 1, we are also going to push it to the top of the stack. But things get a bit more interesting when we get an operator. Because now, what does this operator mean? What does this entire 0, 1 minus thing mean? This means that we have to do 0 minus 1. In other words, we have to pop 1 out of the stack. We have to also pop out 0 from the stack, take their negation, that is do 0 minus 1, because we have gotten a current value as the negative minus sign. So we have to do 0 minus 1 and then put it back into the stack, right? So what did we do? You get an operand, you add it to the stack, no asking questions twice. But as soon as you get an operator, go ahead and remove 2 values from the top of the stack, do the evaluation, and then add them back in. Okay, let me continue and show you what this means. So we get 3. This is an operand, we'll add it to the stack. We get another 3, operand, add to the stack. What do we do when we get a star? As soon as we get a star, we'll pop 1 value out, we'll pop another value out, multiply both of them since this is a star operation, find the value, and push this answer back onto the stack. Okay, again, what do we do when we get a 7? Add this onto the stack. Now what do we do when we get a slash? What will be the next step? Since we have a slash, we're going to pop out the last 2 elements, 7 and 9. We're going to take their division, 9 by 7, and this is a C-style division, so we'll get the answer as 1. So we'll get the answer as 1 and we'll push this back onto the stack. And then finally, we have the plus operation where we'll pull out 1. We'll also pop out minus 1, add them together, get the answer 0, and then push it back onto the stack. At the end of this iteration, one thing is guaranteed. There will be only one single element inside of the stack, and that will be the answer. Okay, so what are the rules formally speaking? We do 2 things. First, if you have an operand, you add it to the stack. Else, you pop the last 2 elements, evaluate them, and then add their result onto the stack again. Alright, so let's go ahead and look at the code implementation of the same problem. This is the problem evaluate reverse Polish notation, which is the same as the postfix notation on LeetCode. Alright, what are we going to do? First things first, initialize a stack, right? The stack is going to be an empty list. I'm also going to define these ops, which is basically going to define for this character, for this current operator represented as a string, as a character, I want to do this operation. I want to do operator.add. For minus, I'm going to do the subtraction. For the multiplication, I'm going to do mul. And then for the division, I am not going to do floor div. Right? These are the two options with us. We have one as true div, which is just a slash, and the floor div, which is actually double slash. So it might look tempting for you to do double slash when it comes to Python code. Although in other languages, you can just do slash and get away with it. In Python, do not do double slash, because that is floor div. That does not work as intended as you want, and is going to give you issues when it comes to negative values. I won't go into much more detail in that. You can go check out some of the links down below. Anyways, what we're going to do next is we're going to iterate over these tokens given in the input tokens. So what was the goal? We have to first figure out if it's operand or not. Now we'll say if the token is not in the operators, that is, if the token is not of plus, minus, multiplication or division symbols, that means it's a integer value given to us. So what we're going to do is we're going to convert that token to an int value and append it to the stack. All right, cool. So now what we're going to do in the else condition is when we have these kind of operators with us. So what we want to do is pop out two elements from the top of the stack, do the computation, and then append the result back into the stack. Now just a quick run through of what's happening. Note that the ordering of these matters a lot. We're first going to pop out n2 and then n1. Again, look at all of the simulation actually, which I didn't explain it back then, but it's something very important. Look at what we have done. Right? So as soon as we get the plus operation, what do? We first pop out this element from the top of the stack, which is going to take the second place. And then we're going to pop out this element, which is going to take the first place. So this one we currently popped out. This guy is the n1 and the element on the right hand side is the n2, right? This makes more sense for division as well as subtraction because they are not exactly commutative. All right, anyways. First we'll pop out n2 and then we'll pop out n1. Whatever the result is, we're going to get it by using this ops of token. That is, whatever this token is, say it's a plus sign. So we'll go ahead into this dictionary and access this operator.add function. And this is going to take in two values again, n1 and n2. Whatever the result is, we're going to append it to the stack. Now, one last thing that we realized was that the stack is going to have only one single element at the end of this iteration, which is going to be the answer. So we return it at the end, and now let's go ahead and test the code out. So we'll run the code once. Okay, looks good. And we'll go ahead and submit this. All right, cool. So this works out. And yeah, this is sort of a formal implementation of evaluating reverse Polish notation. By the way, if this seems too fancy, you can write some manual code here as well. You can just say elif token is a plus sign. Just go ahead and do this, and result will be nothing but n1 plus n2 and something like this. And so you can do elif for all of these sort of cases, right? If that seems too fancy, you can do it this way as well. All right, cool. So this is it. And I'll see you in the next one. Hello everyone and welcome. In this video, we're going to implement basic calculator 1, 2 and 3 all using the same exact code. Believe me, I'm going to do a copy paste like nothing you've seen before. All right. So the first thing we want to do with basic calculator is realize that we have already written most of the code in these two functions. First function is going to convert the infix notation to the postfix notation, and the second one is going to evaluate the postfix notation. Again, both of these functions have been covered in separate videos of their own, which each of their own intuitions, observations, and formal code that we wrote down. In this question, however, we have to write one more function, which is going to do the parsing or the cleaning up thing. So we're going to do and create a read function, which is going to take in the string and return us the infix notation. All right, that is the goal of this problem. Okay, why do we do this, by the way? Look at this. The input we are given is a string. And so we can have a case like 3 plus a bunch of spaces, 1 space times 337. Okay, so nothing too special, but you can see that this is a hard string to work with. Mostly because won't it be so nice if you can actually have a list of tokens that we need to focus on? That is, if you have something like, say, something that gave us 3, then something that gave us plus, then 1, then star, then 337. Won't it be nice if we have an infix notation laid out like this? Right? This will make things a lot simpler because we don't have nasty spaces to deal with and all of the numbers have been dealt with. That is, 337 actually is considered as 337 and not 3, 3 and 7. Right? These are some of the cases that we have to handle. And so what we are going to do is convert and read the string into the infix notation. So the infix notation is going to be a list which will return at the end. How do we go about making this happen? Well, we'll go ahead and write a while loop. So we'll say I equals to 0. And while I is lesser than the length of s, go ahead and keep on doing some computation. The first thing we'll do is clear out all the spaces. So if the s of I, the current character I'm looking at, if it's a space, well, just go ahead and ignore this. I don't really want to mess with this. Elif, what do we do? Well, in the case of space, we simply ignore. But in the case of operators, we can't really do that because we have to add these individual operators to the infix notation list. So what I'm going to say is if s of I is present inside of the operators, by the way, these operators is a variable over here, which is simply just the brackets and the multiplication, division signs, blah, blah, blah. If the current character I'm looking at is an operator, well, then go ahead and add this to the infix list. So I'll do infix.append the current s of I. I'll also do I plus equals to 1. All right, what's the else condition? The else condition is some case where we have a digit like 2 or 234 or 345, things like that. So we have to handle cases like these separately, right? What I'm going to do is I'm going to create a number variable, which is going to be an empty string. And I'm going to say, you know what, while the s of I dot digit is digit, actually. So while the s of I I'm looking at is a digit, well, then go ahead and append this to the number. So I'll do number plus equals to the s of I. And once I'm done with this, oh, by the way, I'll also do I plus equals to 1 always. And once I'm done with this iteration, when this iteration stops, when I get either a space or an operator, I'm going to say, you know what, go ahead and stop at this point of time. And please go ahead and do infix.append the number. One thing that we always check whenever we write these while loops is whether s of I will actually exist or not. There might be a case where this I plus 1 might take it out of the length of the string. So we'll also have to say, keep it limited to that. While I is less than the length of s and this happens, then do these computations. Okay, so we're almost done, but there's one more thing that we have to keep in mind. And this is sort of a, well, kind of a pain implementation that we have to take care of. Because here's the thing, the minus could be used as an unary operation. That is in the case of -1 and sort of minus of 2 plus 3. All of these cases are valid. But in all of the codes we have seen previously, we did not handle these unary operations. So what is a hacky way around this? Again, this is going to be a very hacky way, but what we can do is we can add a 0 in front of it. So as soon as we get an unary minus, we're going to do 0 minus that thing. So in the case of -1, we'll instead write it as 0 minus 1. And instead of minus of 2 plus 3, we are going to write it as 0 minus 2 plus 3. This is going to make the rest of the implementation consistent with our logic. So we'll have to say, you know what, before you do this, please go ahead and check if the s of I is actually a minus sign or not. Because if it's a minus sign, then we need to do some extra steps before we can jump into solution. All right, when is this minus sign an unary operator? This is an unary operator in a bunch of cases. We have to say, first of all, if I equals to 0, then go ahead and do infix.append 0. That is, if this minus sign is the first thing you ever get in the entire string, if it is the first position in the string, then you have to append a 0 before you append this current operator. All right. But this is not the only case. All right, so we can have another case where we say 5 minus of minus 2. All right, so this is a case where the preceding element, where the element to the previous of this minus is actually an opening bracket. So we'll also have to take care of this condition and say that, you know what, if the current minus is at the 0th element is at the 0th place, go ahead and append 0 to the infix before you append the minus. Or we have to say, or if the s of I minus 1, if the previous element, if the previous character was an opening bracket, then what? Then you have to take care to also append the 0. By the way, just to make sure that this I minus 1 actually exists, we have to write one more condition and say that this I minus 1 should be greater than equals to 0, right? So pretty simple. And yeah, I think we're done now. Let's go ahead and run the code once. Oh, by the way, we still have to write all these functions now. So the first thing we'll do is go ahead and read the S string given as the input, and this will get me the infix notation. For the infix notation, I'm going to convert it to the postfix notation. So postfix equals to infix to postfix of infix. And finally, I'm going to return evaluate postfix. All right, cool. Let's go ahead and test this out. Hopefully it works. Ah, god damn it. Okay, it's a typo. Line 20 is digit. Okay, cool. Fixed. Again, hoping that we don't have any issues. Let's just hope that we don't have any more issues. It's going to be a pain otherwise. All right, I'm going to go ahead and submit this. Let's hope. And great, we get it accepted. Cool. So now, as I promised before, we're going to do a massive copy pasting thing. I'm going to Control C, go here and paste this baby over here. Let's go run the code once again. Get it accepted here. All right, cool, looks good. And once finally in the basic calculator 3, let's go ahead and do the submit directly, YOLO. All right, cool. So we get this code accepted in all the 3 questions just by using these simple logics. What did we do? We first read the input string and we sort of cleaned it up and converted the string to a list of tokens. Then we went ahead and evaluated and converted the infix to the postfix notation. And finally, we evaluated the postfix notation. All right, cool. This is it for this video, and this ends the string related section of stack questions. Next up, we're going to look at monotonic stacks, which is more of a mathematical side of stacks. All right. Hello everyone and welcome. This is the start of a section on monotonic stacks. We're going to look at 6 different problems building up our intuitions on monotonic stacks, the reasons why we use them, how do we actually implement them, and template codes that I'm going to provide at the end of this video, which is just going to be of 5 lines. That's right, a 5-line code template that you can use to solve any monotonic stack question. All right, super excited to bring you this section because it's one of the more advanced concepts, but this should feel as easy as we have been building up our intuitions a lot up till now. All right, let's go ahead and get started with a problem statement, which is going to be buildings with an ocean view. This is a problem on LeetCode, and the reason why I've chosen this is because it's a good way to get started with the idea or the reason why we need a monotonic stack. All right, let's go ahead and get started with the problem discussion. We're given n buildings in a line, and their heights are given by the heights of I. So we're given a heights array, and each of these buildings is of heights of I. There's an ocean on the right hand side of this line of buildings, and the building is defined to have an ocean view if, only if, all the buildings on the right hand side are smaller than that. So for a current building, all of the buildings on the right hand side should be smaller than that. Not even lesser than equal to, they should all be lesser than this building's height. Alright, the goal of this problem is to return the indices of the building having an ocean view. Let's go ahead and take a look at an example to understand this better. In this test case, we have 1, 3, 2, 5, 4, 1, 3 as heights of buildings, and I've plotted this out neatly for you. On the right hand side of these buildings is an ocean. And now the goal of this problem is to find all of the indices of the buildings having an ocean view. In this case, we see that the buildings 3, 4, and 6, all of them have an ocean view. Why are these the answers? Look at the index 3. The building at the index 3 has all of the buildings on the right hand side of it lower in height. The building at the index 4 is lower in height, index 5 is lower, index 6 is also lower. Similarly, we can say the same for 4. All of the buildings on its right hand side are going to be lower in height. We cannot say that for 5, that's why 5 is not the answer. And we can say it for 6 since, well, there are no other buildings on its right hand side, so no other building can block it from having an ocean view. Alright, so how do we start to build up to a naive solution? What is a naive way we can approach this problem? Let's go ahead and look at the same test case and we'll try to build our understanding from this. Let's say that I'm going to focus and I'm going to start iterating over every single building inside of the array. I'm going to start from the building at the index 0. Now for this building, I want to ask the question, can you figure out if all of the buildings on the right hand side of it are lower in height? That is, for a current building that I iterate over, I want to iterate over the rest of the remaining buildings on the right hand side to know whether we have all of the buildings lower in height to the right side of it. Because if all of them are smaller, we are going to save this index. Otherwise, we'll skip over this one. So in the case of the building at the index 0, we see that the building just on the right hand side of it is a building of greater height, which means that we go in the else condition and we'll have to skip over this index. The 0 index can never be a part of the answer. Alright, cool. So let's go ahead and iterate further. Let's go ahead and iterate over it. So now we go to the second building. This is the building at the index 1. In this case, what do we see? The building at the building at the index 2 is smaller in height. However, the building at the index 3 is going to block it from having an ocean. So this cannot be an answer either. Similarly, we can say it for 2. But now what happens if we have the building at the index 3? At the building at the index 3, we can iterate over all of the remaining elements on the right hand side and we realize something. All of the buildings are smaller in height, which means what? Which means that this building has an ocean view. So we're going to save this as the answer. Okay, what about the building at the index 4? Can we say the same thing? Yes, we can say the same thing since all of the buildings on the right hand side of it are smaller. What about the building at the index 5? This is not an answer because building at the index 6 is going to block it from having an ocean view. What about the building at the index 6 then? This will also have an ocean view. Alright, so this is the final answer and this looks to be correct. Let's talk about the space and time complexities. The space complexity is order of 1 since we don't really store anything other than the indices of the buildings which are going to be an answer. So the auxiliary space requirement is actually order of 1. It's not order of n. What's the time complexity? The time complexity is order of n squared. And that's because you can see in the first two lines of our logic, we first iterate over A and then we iterate over the rest. So we first iterate over the array taking order of n time, and nested inside of it, we have to do another loop to iterate over all the remaining buildings on the right hand side of it, which is going to take order of time nested inside of it, meaning we have a total of n squared time complexity. Alright, so this is sort of the naive solution that we have in hand, n squared time complexity, order of 1 space complexity. But is there a way we can optimize this solution? This will sort of start to get at the heart of the reason why we use a monotonic stack. Alright, let's not get too ahead of ourselves. Let me actually show you one more thing. So remember how we discussed that every single building can have these sort of other buildings that block it from having an ocean view. For example, I'm going to write this array now. I'm going to say that building at the index 0 is going to register a complaint against the building at the index 1 because the building at the index 1 is going to prevent it from having an ocean view. Make sense? In other words, I'm just going to call all of the representatives of these buildings, say, and I'm going to ask each of them, hey, do you have any complaints about any buildings greater in height to your right? So the 0 goes ahead and gets a complaint against 1. Similarly, 1 goes ahead and says, you know what? The building at the index 3 is preventing me from having an ocean view. I'm not happy either. Similarly, building at the index 2 says index 3 is blocking me. What about the building at the index 3? The building at the index 3 says, hey, you know what? I don't have any issues. No other building is blocking me. I'm chilling out, so I'll just put a hashtag. Similarly, at the building at the index 4. And now what about building at the index 5? Building at the index 5's representative goes ahead and complains that, you know what? Building at the index 6 is going to prevent me from having an ocean view. what we have just discussed in this array right now, this is super important concept, by the way, which will come again later on. This is the idea of next greatest element. For every single index, I have tried to find the next greatest element. Now in this case, if we can find the next greatest element, that means that the building will have a blocked view to the ocean. In other words, all of the buildings which are not blocked, or they don't have a next greatest element like 3, 4 and 6, because all of them are hashtags, because they don't have any buildings to the next of them which are greater than them, all of them will have an ocean view. Alright, so this is an idea which we'll come to later on as well, so don't worry about that too much right now. But keeping this array, green array in mind, we'll try to see and work out a solution. And this is sort of where we'll start to use a stack. Okay, let me go ahead and take you through the idea behind using a stack. So what we're going to do is this. We're going to run a simulation and we'll see what happens, right? So let's go ahead and start iterating from the left to the right as we did before. We'll iterate over all the elements in A. So in the first case, we get a building at the index 0 with a height of 1. And what I want to do is simply append this building to the top of the stack. Nothing too special. But now let's say I get a building at the index 1. So I have this building over here. And now I want to append it to the stack as well. But look on the top right hand side. Building at the index 0 is going to register a complaint against building at the index 1. That's because building at the index 1 has a higher height, right? It has a height of 3 versus the current building at the index 0 has a height of only 1. Which means that this building at the index 1 is going to prevent it from having an ocean view. What I can do is I can say, you know what? Since 0 has no hope left, since 0 is going to get blocked by 1, let me just go ahead and remove this. So what I'm going to say is, if A of I is greater than equals to the A of stack of top, that is, the current element that I'm looking at, the index 1, is greater than the height of stack top, in this case, the height of the building at the index 0, well then go ahead and pop this element from the top of the stack. Because this element has no hope, there is no way it has a right side ocean view, right? So we're going to pop this element out, and finally we can go ahead and append this I to the stack, right? We did an if condition, and now we're going to do the next case after it, which is going to be stack.append I. Pretty simple. Okay, what do we do next? Let's go ahead and iterate further. And now we get a building of height 2 at the index 2. Is the if condition being followed? No, the if condition is not being followed. We are saying that this building's height is lower than the previous one, so it is not going to block the previous one from having an ocean view. 2 is happy, 1 is happy, both are happy. All right. So let's go ahead and append this to the stack. Okay, very simple up till now. Now let's go ahead and iterate further, and we see that building at the index 3 is of height 5. What do you notice on the top right hand side? The building is at the index 1 and 2 both registered a complaint against the building 3, that the building 3 was way too much in height and is going to block us from having an ocean view. Okay, so what do we do in this case? Well, if we follow the if condition, we have if the current element is greater than the stack top element, then we want to pop that element out. So the building 3 will go ahead and kick out the building at the index 2. But remember, it will also go ahead and kick out the building at the index 1, right? Because it's still greater than that. So this is actually not an if condition that we are looking at, right? Makes sense? Because we remove both of these buildings at the index 1 and 2 respectively, we have to write it instead as a while loop. So we are going to say while the current element is greater than equals to the previous elements on the top of the stack, keep on popping these elements out. And once you're done with that, and only once you're done with that, you can go ahead and append this item to the stack. All right, this is very important. We're slowly building up to the monotonic stack idea, right? This is in fact pretty much the entire code you're going to look at, but let's go ahead and run with the simulation so that I can show you one last, like, very beautiful thing that emerges from this question, right? So let's go ahead and iterate further. At the index 4, we get a building of the height 4. Since this building's height is lower than the stack top ones, we can just directly append to the stack. Remember, both of them will not get a blocked ocean view. Both of them will be able to look at the ocean, as you can see on the bottom side, right? None of them is blocking each other. All right, so let's go ahead and continue further. At the index 5, we get a building of the height 1. Again, this building is not going to block the previous ones, so all of these three will be happy, right? All the buildings 3, 4, and 5 currently have a chance to have an ocean view. All of these three are happy. But let's go ahead and iterate further. At the index 6, we have a building of the height 3. Now what do you notice? This building's height is greater than the top of the stack height, right? As you can see on the top right hand side in the array, we also saw that 5 registered a complaint against 6. Because the building at the index 6 had a height greater than that. So we'll have to go into the while loop and start kicking these building outs, whichever of them have a height lesser than 3. Alright, so let's go ahead and kick out one building, and now what do we see? We see that the building on the top of the stack now, after we have kicked out the index 5, the building at the stack top has a greater height than the current one. So this guy can no longer kick out all the buildings. So we'll say that, you know what, I'm done with the while loop. Let me just go ahead and append myself to the stack. And so we have reached the end of the iteration. And what do you see? We get the indices 3, 4, and 6. Again, look on the top right hand side. 3, 4, and 6 were the ones which never had any complaints against any other buildings. All of them were happy, they were living the hashtag life, alright? So what we can say is 3, 4, 6 are going to be the answer. Okay, this is so amazing, right? We were able to build, and by the way, what we've done is, this is exactly what is called a monotonic stack. In fact, this stack specifically is a monotonically decreasing stack. Why is that? Because you can see that the values in the stack are going to be arranged in a monotonically decreasing order. Right? Okay, take some time to digest this. This is super important. We ensured a constraint, and the constraint was hidden inside the while loop. The while loop said that if you get an element that is going to be greater than the stack top, well, you have to remove stack top. Because why? Because we want to have this constraint of buildings arranged in a monotonically decreasing order. Now, why does this work? What is the logical reasoning behind it? What's the intuition behind this monotonically decreasing idea? Assume for an example that the input was buildings arranged in the ascending order. If the buildings were arranged in an ascending order, you can be sure that only the building at the last index is going to have an ocean view. That's because every single other building will have a building on its right hand side, which is going to block it from having an ocean view. On the other hand, if we have an array with monotonically decreasing values, that is say buildings of the height 5, 4, 3, 2, 1, all of them will have an ocean view. And so what we've done really throughout this while loop and this iteration is that we have somehow made this randomness of the array, that is 1, 3, 2, 5, 4, 1, 3, like they were going up and down, up and down, up and down. But using these constraints, we have figured out a way to arrange them or to look at them in a sorted order. We have made sure that these buildings' heights are in a monotonically decreasing order. And this is the heart of the reason why we use a monotonic stack. Because a monotonic stack is going to enforce a constraint upon the stack. Note again that monotonic stack does not give any special properties or powers to the stack. It in fact enforces a constraint, but that constraint becomes so powerful in some questions that it just becomes mind-blowing of how powerful the monotonic stack can really become. Let's go ahead and talk about some of the template codes that we'll use. All right. So let's talk about the monotonic decreasing case. And by the way, what does monotonic mean? Monotonic simply means that it's going to follow a certain order. So monotonically decreasing means that all of the items in the array are going to be arranged in a decreasing order. That is it, right? It's going to say that every single element will be lesser than the previous element, if there is any. All right, so let's go ahead and write the code for it. And this is the Python code. So first thing we'll do is initialize the stack. And second thing is n equals to the length of a. So we generally, we want to use indices instead of elements to append into the stack. Because if we have indices, as we discussed earlier, it's easy to get the elements, but not the other way around. So we're going to store indices into the stack. And we're going to say for I in range of n, that is, let's iterate over every single index. we're going to say you have to do stack.append I. So for every single index, I want to give it the opportunity of being present in the stack. So I want to be able to do stack.append I for every single one of them. I want to push every index onto the stack. But before I can do that, I have to ensure the constraint. I have to ensure that the while loop is executed. The while loop is satisfied, saying that if I get a value, say a of I, a current value, which is greater than equals to the top of the stack. Note again, this is a greater than equals to sign. It says that we can't even allow same values to be on the stack. They have to be in strictly decreasing order. All right. So we're going to see if you get a of I, which is greater than equals to the a of the top of the stack. That is, the current value you're looking at is greater than the value on the top of the stack. Then you need to pop the element out. So in this case, it does indeed happen that we have to pop this element out of the stack. So let's go ahead and pop that out. But is it? No. We have to do another pop operation so that finally we exit the while loop in peace. Right? And once we're done, we can finally go ahead and do the stack.append I. And we can use this logic, so on and so forth. All right. One more quick little thing that I want to mention is if you look at this, I've written while stack and the comparison function, right? Why have I written while stack and? What is the need of checking if the stack exists or not? And that's because of the condition on the right hand side. That's because of the value that we're trying to access on the right hand side, which is the stack of -1. So the stack of -1 says that go ahead and get me the element at the top of the stack. But before we can get that element, we have to ensure that the stack exists. That the value of the stack, that is, there are some elements inside of the stack. Because if the stack is empty, well then you can't really do the pop operations either, right? Now it makes sense. So we have to check if the stack exists, and only then we can access the stack top. All right. So we're going to follow this condition for a monotonically decreasing stack. And by the way, you can write all of this in 5 lines or even lesser if you are fancy enough. But anyways, this is the monotonically decreasing stack. As I promised you, we're going to also talk about a monotonically increasing stack. Now, the only difference ever is that we're going to change the sign in the condition. That is it. I've literally copy pasted the entire thing and just changed one single sign. Because in this case, we realize that for buildings having an ocean view, we have to have a monotonically decreasing array. But in some cases, it might be helpful to have a monotonically increasing array, right? So we have to be able to use decreasing and increasing as the question needs. And so now how can we remember that, these are the signs? Well, let's go ahead and look at this idea that, well, I was very sleepy, so don't judge me too hard on this. But basically what we're trying to do is I'm going to try and compare current with the value on the top, right? This is what I've been doing. And if the current value is greater than equals to the top value, then we need to start popping these elements out in the case of a monotonically decreasing stack. Similarly, in the case of monotonically increasing stack, I reverse this condition and say that if the current value is lower than the top of the stack, then I need to start popping the elements out. Now, the way you can remember this, and again, don't judge me, I was very sleepy when I figured this out, was that you can look at these signs instead like this. Right? So monotonically decreasing means that, the values are decreasing. So you are kind of sad, and you can see that this guy is sad, right? And in the second case, monotonically increasing, there is a smiley face, right? The V means that the guy is happy. And the way you can remember the positioning of the current and top is that this smiley face has a head and the head is basically the top. So that is how I remember this. And basically we have come to the conclusion that yes, in monotonically decreasing stack, you have a sad smiley face with the top on the right hand side of it. All right. Okay, cool. So now let's go ahead and talk about the time and space complexities, because often this becomes an issue for a lot of people, because although this while loop that we have, it looks like it might take it infinite order of time. It really does not. The time is order of n indeed, and the space is order of n too. Now the space is rather simple to understand. Let's say we have a case like 5, 4, 3, 2, 1, 10. So we have a monotonically decreasing order up till the value of 10, right? So as we go ahead and keep on appending these items to the stack, we see 5, then 4, then 3, then 2, then 1 on the stack. So this is the current value of the stack right now. And you can see that For these kind of cases, the complexity will be order of n in terms of space. But now I want you to focus on the time complexity. Each of these elements have been added to the stack once. That is, each of them is going to take order of 1 time to be pushed into the stack. Pretty simple. But now what happens when we get 10? As soon as we get 10, we have to pop out the elements 1, 2, 3, 4, and 5. Right? Because we have to make sure that the monotonically decreasing condition is followed. So as soon as we get 10, we'll have to do the popping operations and pop everything out and only then append the 10. Now here's the thing. Here's the thing I want you to notice. For adding these elements to the stack, for pushing these elements on the top of the stack, took order of 1 time. Removing them or popping them out also took order of 1 time. So every element, in fact, faces 2 operations at most. It is going to get inserted into the stack, going to take order of 1 time, and is going to be removed from the stack, taking order of 1 time as well. What does that mean? That means that every single element will see at most order of 1 time required. In other words, for every single element to be handled, we'll need order of 1 time. And since there can be n elements in the array, we'll need order of n time, right? So this should clear up a lot of things. You can freeze this frame, you can understand the code, you can understand the complexity, and given that this is a monotonically decreasing stack. All right, this is really it for the sample code. And we're going to make use of this a lot. I promise you, we're going to just use this template code to solve hard problems. All right. They're going to seem very easy once we understand this well. All right. I'm super excited to bring to you this series. So let's go ahead and start off with the next problem. Hello, everyone, and welcome back. Let's talk about the problem nearest smallest number on InterviewBit. All right. The nearest smallest number of an element is defined in this way. It is smaller and present to the left of the current element. And if there is none, we have to set its value to -1, right? So the goal of this problem is to return an array containing the nearest smallest element for each element in the array. Again, note that we define it as the smaller element to the current one. That is, if the current value is x, we want a value lesser than x on the left hand side of it. So in case we have an input like this, where we have 1, 3, 2, 5, 4, 1, 3. So I've plotted this out as well, just for the sake of explanation. We will have the answer such as this. For the index 0, the value is hash. That is, there is no such value on the left of it, which is lower than the current one. And so at the end, we'll replace the hash with a -1. Very simple. And take, for example, the index 3. Now the index 3 has a value at the index 2, which is going to be lower than that, right? You can see in the graph that the height of the element at the index 2 is lesser than the index 3 element. So we are going to save the value of that index in the answer array. Note again that we're going to store the value of these indices, not the indices themselves. All right, so how do we start to think about a solution? What is a naive way we can approach this problem? Well, let's go ahead and say that we have the same input and now we want to iterate over A. That is, we'll iterate over every single element in the input array. And for every single one of these elements, we now want to iterate over the left of this element so that we can find the nearest smallest element. And we can say that, you know what, if you can find the smallest element, well then go ahead and save its value. Otherwise, just skip it, put a hashtag or put a -1 over there. So let's go ahead and run a simulation. For this current value 0, we're going to start iterating towards the left. And since there are no values, we can't really do the iteration either. So we'll just say that, you know what, let's go ahead and assign it the hash value. Or in other words, hash is simply -1. All right, let's go ahead and iterate further and see what happens. In this case, we have the index 1 and the value at the index 1 is 3. Now we're looking for an element at the left of this current index, which has a value lower than this current value. Right? So we're looking for a value lower than 3 towards the left. And what do we see? As we iterate, we find that value at the index 0 is lower than this one. So we're going to store the value at the index 0 as the answer for the index 1. And so we have 1 in this case. All right, let's go ahead and iterate further, see what happens. At the index 2, we have the value 2. Now we want to again start iterating towards the left and we want to start to find an answer. We want to find a lower value according to this current value of 2. As we iterate and iterate, we see that the value we get is at the index 0, and that value is nothing but 1. And so on and so forth. We can keep on doing this for every single element, right? Again, note that we're not storing the indices, we're storing the values at these indices in the answer array. All right, but what are the space and time complexities? The time complexity is order of n squared. That's because we first iterate over all the elements in A. And so if there are n elements in A, they'll take order of n time. But for each of these elements, we also want to iterate over the left, taking order of n time inside of it, which means that the total time complexity is order of n squared. And the space complexity is order of 1, since we don't store anything more than a couple of variables. The array that we build is going to be returned as the answer. So in fact, the auxiliary space remains constant. So now the question is, how can we start to optimize the solution? If you remember, in the previous video, we talked about buildings with a right side ocean view. And I introduced you a concept called the next greatest element. That is, any building would complain that the building next greatest to me is going to block me from having an ocean view. So on the top right hand side, we have the complaint array. That is, say for the index 2 went ahead and wrote down a complaint for the value at the index 3, saying that index 3 is the next greatest element and it is going to prevent me from having an ocean view. Now, what are we doing in this example? What are we doing in this problem now? This was the previous one. In this problem, we're trying to find the previous smaller element. So in a way, if you compare both of these approaches, we can start to see there are some parallels and anti-parallels between them. First is the point that we're looking for the next greatest element and the previous smallest element in both of these cases respectively. Focus on the next and the previous part. Next means that we can simply iterate from the left to the right and get the answer. But since we are talking about the previous element in this case, let's go ahead and iterate from the right to the left. Right? This is one thing that is important to note. We're not going to iterate in the same left to right manner. We are actually going to iterate in the reverse direction, because that is going to make the problem a lot simpler since we are finding the previous element. All right. Now the point is, in the first case, in the next greatest element, we were trying to find the greatest element, right? But in this case, we have to find a smaller element. So in the previous one, we used a monotonically decreasing stack. What do you think will be used over here? We'll use a monotonically increasing stack. And of course, in previous question, we stored I in the stack. That is, we were storing indices instead of elements. In this question, we'll do the same just for the sake of parallel and convenience. All right, so here is going to be our monotonically increasing stack. And on the right hand side is the code. You can see that I've done for I in reversed of range of n, so that now we iterate from the right to the left instead of the usual left to right, right? And we'll try to see how the rest of the code works according to this simulation. So we'll first start from the rightmost value, which is going to be the index 6. So we'll go ahead and look at the index 6 and we see the value 3. All right, since the stack is empty at this point, we'll simply go ahead and append this value to the stack. Again, I'm going to append the indices. The values and the heights of these graphs are just for the sake of demonstration. We're going to store only the indices. Okay, cool. So let's go ahead and iterate further from the right to the left. And we see that at the index 5, we get the value 1. Now, if we look at the condition over here, it says that while the stack exists and the current value is lesser than the top of the stack, then we have to do stack.pops. Now, why are we doing this again? Remember that we have to maintain a monotonically increasing stack, which means that we can't allow the values lower than the current one to come into the stack. In other words, we have to do a stack.pop operation. So we'll pop the element 6 out. That is, we'll pop the index 6 out. And what will we do? Let's go ahead and remove this. But at the same time, what have we found? Notice that this is very important. For this current element we just popped out, we have actually found the answer, right? Because what were we looking for? What was the goal of this problem? The goal of this problem was to find the previous smaller element. And for this current element 6, what have we found? Since we have found the value 5, the index 5 currently, we have in fact found the answer, because the value at the index 5 is lower than the value at the index 6, right? So as soon as we go into the while condition, we are going to pop out the element and then assign it the answer. So the answer of stack.pop is actually a of I. Make sense? Okay, this will make sense again as we run through the simulation more and more. You'll get a better understanding of it. Anyways, the index 6 was popped out, so only 5 remains, and we're going to add 5 to the stack. Again, simple. Let's go ahead and continue iterating, and we see the value 4. What do we do at this point of time? Remember, we have to maintain a monotonically increasing stack. So since 4 value is greater than the value at the 5 index, let's just go ahead and add this to the stack, right? Simple. Okay, now let's go ahead and iterate further, and we see that the index 3 has a value 5, again greater than that. So this works out. Just add it to the stack directly, and look at that. We have a neat monotonically increasing stack. All right, now things will get interesting once again, because as we iterate, we see that the index 2 has the value 2. Now look at the value 2. The value 2 is lower than the values of the indices 3 and 4. In other words, this is going to kick out the index 3. Make sense? And what does it mean for 2 to kick out the index 3? It means that for 3, 2 is actually the previous smaller element. All right. So as soon as 2 comes in, it is going to kick out the 3. We are going to the while loop, and we are going to pop the element 3 out of the stack. And then the answer of 3 becomes what? The value at the index 2. So look in the top and right hand side, and we see that the index 3 has the value 2. All right. Now let's go ahead and continue doing this. And we're still inside of the while loop, by the way. And what do we see? Again, we see that a of I is lesser than a of the stack of top. What do we do? Pop out the element of the top of the stack. And what have we found? We have found the previous smaller element for the index 4. Right? So smart, right? So what we're going to do is we're going to say, you know what, pop this value out. And the answer of 4 is also going to be the value 2. It's going to be the value 2. Again, remember that this kind of messing around with the indices and all. So remember that stacks always store the indices, but the answer array is actually going to store the values. So instead of storing answer of stack.pop equals to I, we're going to do a of I. That's the only detail you need to take care of. All right, let's go ahead and continue iterating, see what happens next. All right, we'll add 2 to the stack. Again, you can see that this is a monotonically increasing order. All right, so let's go ahead and iterate further, and we get at the index 1, we have the value 3. Okay, pretty cool. Since again, this is greater, monotonically increasing fits well, let's go ahead and append this directly. Okay, now things are going to get interesting once again, right? What I'm going to do, we'll iterate further, and at the index 0, we see the value 1. What does this mean? This means that we have found a of I, which is lesser than the stack top value, right? What does that mean? We have figured out for the value for the index 1, we have the value at the index 0 as the answer. So we pop out the index 1 from the stack and assign its answer. So now go ahead and look at the top right hand side, and we'll see that the index 1's answer is going to change to the value 1. Why is it going to change to the value 1? That's because the value of the index 0 is 1, right? The a of I is 0. Sorry, the a of I equals to 0 is 1, right? Cool. So again, are we done with this while loop? We're not done yet. So we'll have to do one more pop operation, assign the value of the index 2 to be 1 again. All right, cool. So now what do we do? And this is a very, very important point. Remember, we can only say that an answer exists for an element if we have found a previous smaller element. Now look at the index 5. In the input, the index 5 has a value 1. And currently we are at index 0, also having the value 1. So can we say that we have found an answer for the value at the index 5? No. Why not? Because we are looking for a smaller value. The element at the index 0 should have been lesser than 1, and only then we could have assigned it a value. But since both of these are exactly the same, we can't really say we have found an answer for 5. And so we'll have to append it directly. And so this is the reason why, even though we are going to use a monotonically increasing stack, that is what we'll call it, but this is not a strictly monotonically increasing stack. In other words, it's simply a non-decreasing stack. In other words, we allow indices of the equal heights to be present inside of stack. That is the reason why we don't have an equal to, and that is the reason why we have made that small change in the code. Again, makes sense. We have run through the entire simulation and now everything should make sense. And since we are actually done with the iteration, we can say that we have not found the answers for the indices 0 and 5 because they are still in the stack. We never found any previous smaller elements for both of them. So let's just go ahead and formalize this, clear this out. And this is the input, this is the output. Now, one last thing that we do is for whatever values we have not gotten an answer, we're simply going to write -1 in their places. All right, so at this point, we have looked through all the code. It's time to actually implement this. So let's go ahead and start implementing. We'll go ahead and create a stack. And remember, this is going to be a mono increasing stack. But keep in mind, we are not going to follow the the less than equals to condition. We are going to follow the less condition, right? Cool. So let's go ahead and start iterating for all the elements in the range of n. N is the length of A. Now, is it going to be the range of n? Remember, we're looking for the previous smaller element. So we actually have to reverse the range, right? Because we're looking for the previous element. Now what I'm going to do, I want to give every single element a chance to exist. So I'm going to do stack.append. But at the same time, I want to check, hey, while the stack exists and the A, I want to compare the A of I condition with the A of stack of -1. I want to do some computation in this case. Now, what is this condition going to be? We're looking at a monotonically increasing stack. What did I tell you in the last video? Monotonically increasing means we are looking at a smiley face, which we have something like this case. But as I already explained, we're looking for a previous smaller element. We're looking for strictly lesser elements, which is something why we'll do this lesser than sign over here. So let's go ahead and write this lesser condition, not lesser than equals to, is just lesser, right? And now we want to do something over here. Obviously, I want to pop this element out on the top of the stack. But for this current element that I just popped out, I have gotten the answer. So the answer of this guy is actually the A of I. And at the end, I want to return the answer array. By the way, this answer array is going to be initialized with -1s all over n. Basically, I'm going to say for all of the n values, I'm going to assume I'm never going to get an answer. And so as we get the values for each of these indices, we are going to assign and replace the -1s. All right, cool. This looks okay to me. Let's go ahead and test this out once. Cool, this works out. Let's go ahead and submit this. And cool, we have the solution accepted. So this is it for the solution to the problem, nearest smaller element. Hello everyone and welcome back. Let's talk about the problem trapping rainwater, which is present on both LeetCode and InterviewBit. Alright, let's first talk about the problem setup. We're given heights of bars representing an elevation map. And so in the below case, you can see that there are a bunch of heights. And the goal of this problem is to return the amount of water trapped after raining. So let's say that throughout the night it rains, and this is what it looks like in the morning once again. Alright, so we have to return the amount of water trapped. So let's go ahead and look at the amount of water trapped in each of these individual water bodies. So we have 1, 4, and 1 units of water trapped respectively. This gives us the total as 6, and 6 is the value we return as the answer to this test case. So how do we start to think about this problem? And to be honest, this is not exactly obvious what do we do, right? This is a bit complicated problem. However, let's try to break it down and see what has happened. Maybe we can figure out something that is crucial for this solution to work. All right, so if we focus on this part of the elevation map, what do we see? Well, after it rains, we see that the water is filled like this. And the heights of these are as follows. We have 2, 1, 0, then 0, 1, 2, 3, right? So there is something, it looks to be something like we have to expect a decreasing order of elements first, and then an increasing order of elements. And this looks to be the case in this particular section of this elevation map. And it sort of makes sense logically as well. Let's say that you are in a bunch of mountains and there are a bunch of valleys. Where will the water be stored after it rains? The water will obviously be stored in the valleys. So by figuring out the decreasing and the increasing sequence of elements, perhaps we can get closer to the answer. All right, maybe this is a special case. What happens if we focus on, say, this area? This area also shows the same thing, because we first have a decreasing order of elements, that is 1 to 0, and then an increasing order of elements from 0 to 2. Interesting, right? All right, let's look at what happens on the right hand side of the elevation map. We have something like 3, 2, 1, and then 1, 2. So we see that this logic of first finding the decreasing order of elements and then an increasing order of elements seems to be correct. Now, can I say that we can also split them out into two cases like these? Can I say that if I have 3 to 1, it will also store some water? No, because see, if it rains on this kind of test case, like where it's just 3 to 1, in this kind of elevation map, the water will just flow right off from the right hand side. Right? So it's not always that we have to find a decreasing sequence of elements. It is not enough to just have a decreasing sequence of elements. On look at the test case on the right hand side, we see that there are values 2 and 3. So we have an increasing sequence of elements. Again, after it rains, what do you note will happen? The water will just come in and flow on to the left hand side, which means that it's a combination of both decreasing and then increasing sequence of elements which is going to make the answer work. Now let's say that it actually does rain and we have a test case like this where we have 3 to 1 decreasing and then 1 to 3 increasing present. What would happen in this kind of test case? In this test case, as it rains throughout the night, the first thing that will happen is there will be some water that is formed above the element 1. So these 2 and 2 on the left and the right hand sides sort of act as the left and right boundaries, defining the width of the amount of water we can store. In fact, these 2 and 2 also define the amount of height of water we can store, which is the upper limit of the height is going to be 2. And the lower limit of the height of this water body is going to be defined by the element it's sitting on top of. In this case, it's the element 1. So as it rains throughout the night, we also see that another level of water starts to appear. All right, so this time is bounded between these 3 and 3. Again, the upper bound is the height 3 and the lower bound of this sort of rectangle of water is the height 2. All right, so we're trying to formalize this and it seems like we're getting somewhere, right? There seems to be something interesting about these finding these left and the right boundaries so that we can figure out the width of the water body. And then we can figure out the top and the bottom of like the defining and the heights. So we can figure out the top and the bottom of the heights, and perhaps just by multiplying these width and the height values, we can get the answer. One more thing, this is an interesting thing that happens. What if we have a 4 on the left hand side? Note that the height of water remains the same, because the height of the water, the upper height of the water, is defined by the minimum of both of these guys, right? So we'll also keep this in mind. This is a special interesting thing that is going to happen. And now let's go ahead and formally talk about the optimized solution. Now again, let me remind you, what have we noticed? What is the invariant that we saw? We first need a decreasing sequence of elements followed by an increasing sequence of elements. So how can we model this decreasing sequence of elements first? What we can do is we can use a monotonically decreasing stack to simulate this kind of thing. So let's say that 0, 1, 2, 3 all have these decreasing sequence of elements. And so this is what we're going to start off with. Of course, the code for monotonically decreasing kind of stack is something we've already seen before, and this is the exact copy-paste implementation of it. If you aren't familiar with this, I'll highly suggest you go check out my previous videos where I've described this template code in much more detail. Anyways, what would happen next? What would happen, say, if at index 4, I get a value smaller than that of the index 3? So it'd be like continuously decreasing, so it's still okay. So nothing really special will happen if I get another decreasing value. Again, remember that it's not just that we have to have a decreasing sequence of elements. There should be a decreasing sequence of elements followed by an increasing sequence of elements. Right? We'll keep that in mind. Now, if we get a value lower than the value of 3 next up, well, nothing really special happens. But let's say that we get a value at the index 4, which is greater than the value of 3. Now, what do you think will happen in this test case? Well, obviously, since this is a stack question, we want to try and append this I to the top of the stack. But we won't do that just yet. We'll hold on to it. And I've just marked it with dotted lines so that it's clear I have not appended to the stack yet, but it is still there. I'm going to think if it's there, what would happen? Okay, so what would happen in case we get an element 4 like this, right? So as soon as the rain starts happening, what will you notice? As soon as the rain starts happening, the 2 and the 4 will actually form the left and the right bounding indices for this width of the water. Make sense? And both of these heights, along with the height at the index 3, are sort of going to define the height, the overall height of this puddle of water. Right? So something really interesting is happening over here. In fact, what I can say is the 2 index is sort of acting as a left bound and the index 4 is acting as a right bound to it. So what I'm going to do is I'm going to relabel some things. I'm going to say that for I in range of n gets changed to for r in range of n. Basically, for every single current index that I get, I'm going to assume it's the rightmost index. It's the right bounding index. Saying that this right index is going to try and find another left index so that we can trap some water in between those widths. All right. So what are we going to do next? Well, as soon as we go into the while loop, we see that we have to do a stack.pop operation, which means that this element that we're currently looking at has to be popped. I'm going to call this element m since it's present in the middle of these left and the right bounding indices. Again, the left is the 2 and the right is the 4. So once I have popped out this m element from the stack, what is the stack top? The stack top is going to be this element, which is nothing but the left bounding index. So what do we have here? We have a case where after we pop out one element from the stack, that is the m element, we have the stack top currently acting as a left bounding index, and the r, which is the current index I'm on, is the right bounding index. Which means that in a way, I've actually found the width of the water trapped. Pretty amazing, right? So what is the width going to be? Well, we're going to do 4 minus 2, but we'll also have to do minus 1 because of computational reasons. Basically, r is 4 and the L is 2. And what is the width of the water trapped? It's actually 4 minus 2 minus 1. All right. So this is a small implementation level detail that you need to take care of, but it's pretty simple. All right. So we have the width of the water with us, but now what is going to be the upper height of the water? Is there a way we can figure out the upper height of the water where it can be at most? As we discussed earlier, the upper height of the water is going to be defined by the minimum of the left and the right values. So I'm going to take the minimum of a of r, that is, look at the right value, and then go ahead and look at the left value as well. So which is going to be nothing but the stack top. Again, what is stack top? Stack top is going to be the L. So stack of minus 1 is nothing but L. It's the left bounding index. Okay, cool. So now that we have the upper height of this water, can we just directly multiply the width and the height? No, not yet. Because along with the upper level of the height of the water, we also have to figure out the lower height of the water. Because look at that, the A of m, the element sitting at m is going to eat away at some of the water we can have. Make sense? Imagine this, if the A of m was lower in height, then we could have much more water, right? So this A of m is going to eat away at some of this current height that we have. In fact, what we're going to call it is, we're going to say we have some leftover height after we remove the current height of the minimum of left and right. And we say minimum of left and right minus the A of m. So this is the leftover height we have with us, and we already figured out the width. So now what do we do next? Okay, this is the fun part. What we do is we can figure out the area of the water now, because the area of the water is nothing but the width times the leftover height. And we can simply take this area and add it to the total. So on the top right hand side, we'll keep a track of the total. And what will happen in this case? We see that the width is 1 and the height is also 1. So we're going to say that total now increases by the value 1. Again, all of this was keeping m mid in mind, right? We had to keep the mid in mind. But the current stack top is what? It's the value at the index 2. Okay, so now this pops out and we can iterate further. What do we see next? As soon as we enter the next iteration, we figure out that m equals to 2 and the stack top is at the index 1. All right, so what do we do now? Again, let's go ahead and follow those steps. We have to first figure out what is the width of the water we can store. What is the width of the water? It is nothing but the left and the right's difference minus 1. So we're going to take the right bounding index, we're going to subtract the left bounding index, which is the stack top, and then we'll do a minus 1. What does that mean? We have something like 4 minus 1, minus 1. So in fact, the width of the water is going to be 2. What is the height of this water? The height, we have to consider the leftover height again, which is going to be the minimum of the left and right bounding indices, and we'll have to subtract a of m from it. So again, in this case, the leftover height comes out to be 1. So now we have the width and the leftover height in place. What can we do next? We'll simply multiply them together, get the area, which is going to be 2, and add it to the total. So now the total becomes 3. And this is the kind of structure we have. And just by the way, before we append this R to the stack, because now we can do that, let's go ahead and take a look at what happened. What happened right now? What we just saw was this kind of test case, right? We can see that this is exactly something we figured out earlier on as well. The water, as it rains throughout the night, is going to fill up level by level. And by using a monotonically decreasing stack, we were able to exploit the property saying that if we got any other higher value to the right of it, then we have found the bounding indices, because we already have the left bounding indices and now we have found the right one as well. So this is the way we can work towards a solution. And really, this is it. So what we can do is just append this R to the stack and then we are done. So we can do and follow this kind of logic to get the solution. Okay, so let me go ahead and actually show you one last thing that we missed, and look at this fact. All right, whenever we are talking about width, we're doing R minus the stack top, which is the left, minus 1. Now, all of this assumes that the stack top is going to exist, but it is not always the case that stack top will exist, right? This is something we have seen again and again. This is a special edge case. So we have to say that if the stack does not exist, what do? Think about it this way. We don't have a left bounding index anymore. What does that mean? That means that if it rains, all of the water is just going to flow away. There is nothing on the left side to bound it. So we can say that, you know what, just skip over this current while loop and say that, you know what, the stack is empty. We can't really bound anything. No water is going to get trapped if the stack is empty. All right, cool. So this is really it for the code, and let's go ahead and see how to implement this from scratch. All right, cool. So we're going to start off with the stack, which is going to be an empty list, right? We're going to have n equals to the length of height. And we'll start to iterate for I in the range of n. Cool. All right. At every single point of time, I want to do stack.append I, because I want to give every single index an opportunity to be in the stack. But at the same time, I have to ensure something. While the stack exists and the stack top is in some condition with the A of I, right? If we have something like this, we have to take care of the condition now. What is the condition going to be? We're talking about what? We're talking about a monotonically decreasing kind of stack, which means that we have a sad smiley face. So we have we have greater than equals to over here. And just by the way, I'm also going to change this height to A, just for the sake of convenience and explanation. And this I, as we already saw, was actually R. So I'm also going to change this I to R. All right, cool. So now what do we write in the while condition? We first pop out the stack top. So we'll first figure out what is the middle element. And now we'll say left equals to the stack top. Before that, we'll also say if not stack, break. We have to ensure that the left bounding index is actually present. Now, if you have found the left bounding index, right? So what is going to be the width? The width is nothing but the right minus the left minus 1, right? Again, this is an implementation level detail that we figured out earlier on. All right, so now we have the width, and what is the height going to be? As we discussed, the height is going to be the minimum of the left and the right bounding indices. So we'll take the minimum of A of R and the minimum of stack top. Cool. All right, now we can figure out finally the leftover height, which is going to be nothing but height minus the area that A of M eats away. So A of M eats away something, and then we finally have total plus equals to the width times the left over height. Alright, cool. So now we can return the total at the end. We'll also initialize it over here. And let's go ahead and run this code once just for a quick sanity check. Cool, looks like it works. So let's go ahead and submit this. And we get it accepted. Alright, cool. So this is it for the solution to the problem, trapping rainwater. Hello everyone and welcome back. Let's talk about the problem, largest rectangle in histogram. This is a problem present on both LeetCode and InterviewBit and is a very common interview question. Alright, let's go ahead and talk about the problem setup formally. We're given an array of heights in the form of a histogram. The width of each bar is going to be of the size 1. The goal of this problem is to find the area of the largest rectangle present in the histogram. Alright, let's take an example. We're given this array as 1, 3, 2, 5, 4, 1, 3. So this is the input array of heights given to us, and below is the visualization of how it's going to look. The answer, that is the largest rectangle we can have in this histogram, is this. So it's a rectangle of the area 8, right? So this is going to be the answer. We have to return 8 as the answer. Okay, so now how do we start to think about a solution? What is a naive way we can approach this problem? All right, let's go ahead and take a look at the same test case. And what I'm going to do is I'm going to define something called a span, right? So this is the idea over here. For an element like say the index 4, on the index 4, we have the element 4. And what I want to do is I want to focus on this current rectangle over here, right? So the current rectangle, this is the area I'm going to look at, fine? So this is the current rectangle. This is the current bar I'm looking at. What I want to do is I want to expand this. I want to take this rectangle and stretch it in both the directions. So I want to first stretch it in the right direction, but I see that down below is actually a value 1. So at the index 5, the value decreases from 4 to 1, which means that, this sort of restricts my movement in the terms of right direction, right? But what if I want to expand it towards the left? If I want to expand it towards the left, I can, because towards the left, there is a value higher than this current one. All right. So in this way, what I've done is from this original input that was given to us, we're trying to stretch this current rectangle in both the directions, left and right. We couldn't extend it towards the right, but because, there was a lower element present, but we were able to extend it one step towards the left. By the way, we can't extend it towards the left anymore either now, because again, there is a lower value present. So these sort of lower values are going to restrict what is the span of this current rectangle. In fact, let me go ahead and formally define the right span and the left span. Now, in this case, what we have done is we have said that the right span is going to be r minus I minus 1. Now, r is going to be the first right index where the value decreases from the current value. That is, if you're looking at the value 4, right span is going to be marked by r, which is going to be the first value that is lower than 4. Similarly, for the left span, we'll have something called L, which is going to be the left value where the value decreases from 4. So we see that the left span is defined by the index 2, that is L equals to 2, and the right span is defined by R equals to 5. Now the exact value or the distance of the right span is going to be what? Is going to be R minus I minus 1. For the left span is I minus L minus 1. All right, let's take a quick example. If we look at this test case itself, we see that the R is 5, I is 4, as I've marked in the input as well. And we have to do 5 minus 4 minus 1. This means that the right span is 0. And that is exactly what we see here. We can expand this current rectangle 0 steps towards the right. All right, pretty simple. What about the left span? The left span is 1. We can already see that the left span is 1. But why is that? That's because we do I minus L minus 1. I is 4, L is 2. And we have to do 4 minus 2 minus 1, which is equal to 1. Now, if I ask you the question, what is going to be the total width of this rectangle after we have done the stretching? After we have done the stretching, the width of this rectangle is actually going to be the left span plus the right span plus 1. Wait a second. Why are we doing plus 1? Because here's the thing. The right span is going to define the fact that we can expand this rectangle 0 steps towards the right. Left span says that we can extend it 0 one steps towards the left. But we already have to consider the current rectangle itself. Make sense? So we have to do left plus the current one plus the right. And that is going to be the total width we have. All right, so the right span is going to be r minus I minus 1 and the left span is I minus L minus 1. The total width is nothing but both of their sum plus 1 to include the current rectangle itself. Okay, this is, by the way, the heaviest part of the video. This is the most of terminology we are going to use, but things are going to get much simpler later on. All right, just to get comfortable with this, let's go ahead and take another example. Let's say we are looking at the index 2, which has the value 2. Now, how can we find the left and the right span? Well, let's go ahead and shade this rectangle. So this is the rectangle I've marked in yellow over here. And now I want to stretch this out in both the directions. So how much can I stretch it? Well, if I want to stretch it towards the left, I'm going to see that I can stretch it 1 unit. And towards the right, I can stretch it 2 units. Right? So this is the answer we get. In this case, L equals to 0 and R equals to 5. Right? I've marked both of them with circles. So what is the span going to be? The right span is going to be 2. The left span is going to be 1. And the total width is going to be 2 on the right, 1 on the left, and 1 itself. So 2 plus 1, which is 4. And that sort of makes sense now, right? So now I want to ask the question, how can we figure out a solution to this problem using this kind of span approach? What we are going to do is we're going to iterate over A. This is the first step. We're going to iterate over every single element in A. We are going to iterate over every single bar in the array given to us. Now for any current bar, I want to go ahead and find the left span and the right span, right? So as soon as I get to the left span and the right span, what do I know? I know the width of this current rectangle. And what is the area going to be? The area is simply going to be the height of the current bar times the width. Because we were able to take the height h of the bar and we were able to expand it to width w. Okay, now it should start making a lot more sense. And what we can do is we can iterate over every single element in the array, again asking the question, taking this, what is the span of this current element, right? And every single time we can store the area, and then on the top right hand side we have the answer, which is simply going to be the maximum of all the areas. Because remember, what's the goal of this problem? We have to find the largest area rectangle in the histogram, right? So this is the way we're going to approach this problem. Okay, cool. So let's go ahead and take another example. In this case, we have the index 2, and as we already saw, we expand it in both directions, left and right, and this is the area we get. So the answer becomes 8. And in fact, this is one of the possible solutions giving you the answer 8, which is the maximum possible area you can get from this histogram, right? Okay, cool. So let's talk about the time and space complexities of this solution. And what we're doing is, we're first of all iterating over the A. We're iterating over the array, which is going to take order of n time, where n is the number of elements. But for each of these elements, I want to go ahead and expand in the left and the right directions, right? So I want to iterate again for every single element in the left and the right directions to know the spans, to know how much I can expand this current rectangle to, which is going to take order of n time each for every single element. Which means that we're looking at a time complexity of order of n square. The space complexity is order of 1 since we don't store anything more than a couple of variables. So is there a way we can optimize this time complexity from n squared to order of n perhaps? Let's go ahead and talk about the optimized solution. Now let me ask you the question, what are we doing? For any given index I, for any element at this index, what is the goal of this problem? Remember, we want to expand both the left and the right directions, and we want to find the span of this I. That is, for this current value, I want to know how much I can expand in both the directions by finding the values L and R. Now, what are these values L and R? L is the left value, which is lower than this current one, and R is the right value, which is lower than the current one. This kind of structure is something we can try to simulate using a stack. So let's go ahead and take a look at what would happen if we use a monotonically decreasing stack. Right, on the right hand side, I've also provided the code just for the sake of reference. Now, if in the case we have a monotonically decreasing stack, let me ask you the question, what would happen? for any given element, since we want to find the right and the left places where it decreases for the first time, if we have a monotonically decreasing stack, we can always look on to the right hand side to know if a value has decreased or not, right? See, again, let me go back to this. The entire point of this kind of span idea was to find lower values, and these are going to be the bounding values. As soon as we get lower values than this current I, it's going to prevent us from expanding further. So won't it be nice if we have these kind of values with us, right? And so this is the reason I'm going to say that if we have a monotonically decreasing stack, you can simply look to the right of this element to know the first value where it decreases. So the right span is actually super easy to compute with the monotonically decreasing stack. However, there is an issue. How do we find the left span? The left span is going to be given by the left value, which is going to be lower than the current one. But in the case of a monotonically decreasing kind of stack, how do we get that? We have obviously a decreasing order of elements, which means that no element to the right of this element, this current element, will be lower in value. Which means that perhaps monotonically decreasing stack is not the right way to go. And what we want is actually a monotonically increasing stack. All right, so again, I have to mention what have we done. I want to also focus your attention on the right hand side where we change the code a bit, because now the condition becomes less than equals to instead of greater than equals to. Anyways, now what do we do in the case of a monotonically increasing stack? Let's go ahead and run a simulation because it's going to make a lot more sense. Okay, let's say that we get an element like this. What do we do next? For the current element present at the top of the stack, as soon as we get a lower element, we have found a right span, right? And how do we find the left span? The left span is just an element to the left of the stack top, right? It's so cool because by looking at a new element that just came into the array, that wants to be added to the stack, we were able to find the right span of this current element. And we already have the left span present with us because those are going to be the values inside of the monotonically increasing stack. So in this way, we have actually found the answer for this current element, right? Because we know the left and the right bounding indices. We know now the places where we have lower values than this current one. So we can stretch out the rectangle up till, but not including both the left and the right boundary conditions. In fact, what we have done is the current bar, the current yellow guy that we have right now, is actually going to act as a rightmost bounding element, right? So I'm just going to change all of the i's to the r, which will make the implementation a bit simpler. Because what we're going to do next is we're going to pop the element out of the stack. Look at the while loop's first line. As soon as we get a condition where we find a lower element than the stack top, we have to pop this element out of the stack. And what we'll do is we'll call this element I. Interesting, right? It's not the R that is going to get us the answer. It's the I that is going to get us the answer because I is the real focus over here. And now what is the L going to be? Think about this. L is going to be the value on the left hand side, which is lower than this current I, which is nothing but the value we've added on to the top of the stack already. So the L is actually going to be the stack top. Again, this is because we have a monotonically increasing kind of stack. Feel free to pause here because what we have done is very, very crucial to understand the rest of the solution. In fact, this is pretty much the heart of it. Okay, cool. Now there's one more edge condition that we have to take care of as usual, because here's the thing. It's not always the case that the stack top will exist. So what do we do? Well, we can do L equals to stack top if the stack exists, else we'll set it to -1. That is, if we do not have a left bounding condition for this current rectangle, we are going to set it to -1 by default, which is going to be present just beyond the y-axis that you see on the left hand side over here. Why is that, by the way? Okay, that will make sense once we go further along because you will understand the simulation better. But for now, just assume that we have to set it to a default value, and that default value is present to the leftmost value that we can get. And that is going to be -1. Anyways, now what do we have? We have the L, which is the stack top. We have the I, which is the current element that we just popped out of the stack. And we have R that we're iterating over. So now that we have L, I, and R, what can we do? Let's go ahead and write this down a bit more cleanly. What we are going to do is now we can say that we have found the right span and the left span. Because again, I'm going to follow the exact formulas that we discussed earlier. R minus I minus 1 is going to give me the right span. I minus L minus 1 is the left span. And then what is the width? What is the width? The width is the left span plus the right span plus 1. And now what is the area going to be? We have already found the width. Now what is the area going to be? Area is going to be the height times the width. Now what is the height? Height is the height of this current ith value. So we're going to do A of I times width to get the area. And simply speaking, since we have to find the maximum area of all these possible i's, we have to do answer equals to the max of answer comma area. And this is it for the code. I'm not kidding, right? This is such a complicated problem, but we have found such a neat, logical way to think about the code of this solution. All right, let's quickly discuss the space and time complexity of this solution. Since we are using a stack, we'll have to use order of n space in case we keep on adding these elements to the stack without popping them. But the worst case time complexity is still order of n because any element will at most see two operations, addition to the stack and removal from the stack. And since every single element is going to see two operations of, well, order of 1 time each, all of the elements in total will take order of n time in total. All right, so let's go ahead and implement this once more and things will become a lot clearer. We'll go ahead and initialize an empty stack and we'll start appending for R in the range of n. What is the n? N is going to be the length of heights. All right. By the way, again, just so that it is implementationally consistent, I'm going to relabel the heights to A. A is the array we are given to us, right? Okay, so for every single element, I want to give it a chance to exist inside of the stack. But before that, we'll also check while the stack exists and the A of this current value is what is following some condition with the A of stack top. All right. We'll do pass over here. Now, what is this condition going to be? What is the kind of stack we want to have? We want to have a monotonically increasing kind of stack. Again, look at the previous ones. We have a monotonically increasing kind of stack. All right, cool. So now what do? The condition is going to be what? Since we have a monotonically increasing stack, we know that there should be a smiley. So we have less than equals to over here. Cool. All right. So now we want to first figure out what is the element at the top of the stack, which is going to be the I. All right. So I is going to be the stack dot pop. Cool. What is going to be the L? L is now going to be the stack top, but it's only going to be the stack top if the stack exists. Else, what do we say? Else we'll have to set it to default value to -1. You can think about this line a bit more because I know this might seem a bit complicated, but it's actually very simple. All right, cool. So now we want to find the right span, which is going to be R minus I minus 1, and the left span, which is going to be I minus L minus 1. What is going to be the width? The width is the right span plus the left span plus 1. Again, right span is the right side of the area where we can expand to. Left span is the left area we can expand to. And we have to do +1 to include the current bar itself. And now what's the thing we're going to do? Area is going to be the width times the current height, which is going to be the A of I. And we're going to say answer equals to the maximum of answer comma area. And we'll have answer equals to say 0 over here, which will return at the end. Cool. So let's go ahead and run this code just to see if everything's okay. And we can go ahead and submit this. All right, so we get a wrong answer. Wait, why is that? We followed the logic perfectly, right? What did go wrong? Here's the thing. The input is 2, 4. Look at the input. The input given to you is a monotonically increasing stack. What it means is we never got a value which was lower than 4 to kick out these elements from the top of the stack. In other words, what we have is a case where at the end, the stack sum still has some values. And this case is going to be 2, 4. Now we somehow have to figure out a way to kick these values out of the stack as well, so that we can actually go ahead and consider this. So this is a implementation level detail as well. And what we can do is, it's a very sneaky way to do it, but we can append minus infinity, or if you want, you can also append 0 at the end of the array. What will this do is this will force push all of the elements from the stack, all of the remaining elements from the stack. All right. So this is going to kick out 4 and then it's going to kick out 2. So we have to somehow force the elements from the stack. This is an implementation level detail. So this is a very small detail, but an important one, right? Okay, cool. Let's go ahead and run the code once again. That looks to be correct. And we'll go ahead and submit this. And cool, we get it accepted. Hello everyone and welcome back. Let's talk about the problem sum of subarray minimums. Now before we dive into this solution, I have to mention, if you haven't watched the video on largest area rectangle in histogram, I'll highly recommend you go and watch that first, because this question is going to borrow a lot of ideas and code from that question. In fact, you'll slowly realize that this question is a slight bit variation on that one only. Okay, enough talking, let's go ahead and get started with the formal problem discussion. Right, so we're given a simple array as the input, and the goal of this problem is to find the sum of minimums of each of the subarrays. So in the case we have 1, 2, 3 as the input, the output is 10. That is because we can first of all enumerate all the subarrays. So we have the subarray single element 1, 2, 3, then we have 1, 2, 2, 3 and 1, 2, 3. Now of all of them, we are going to figure out the minimum value of each of these subarrays. So we have 1, 2, 3, 1, 2, 1, right? And the only thing left to do is add them all up and return that as the answer. All right, so this is the general idea of the problem. This is what is expected to be done. Now, what is the naive solution? What is something that we can do right away? Let's go ahead and take a look at an example. In this case, we have 1, 3, 2, 4, 3. Since the goal of this problem is to return the minimum of all the subarrays, well, the sum of the minimum of all the subarrays, what we can do is first enumerate all the possible subarrays. So we'll write down all the subarrays of length 1, all the subarrays of length 2, of length 3, and 4, and 5. I know this looks beautiful, but obviously there's kind of cumbersome. In fact, even in going through all of them, it'll look like too much work. Anyways, we're still not done. Because while the first step was to enumerate all the subarrays, the second step is going to be finding the minimums of each of these resultant subarrays. So we're going to go ahead and iterate over all of them and figure out the minimums. And only once we have them, we can sum them all up together and return that as the answer. Now, if we talk about the space-time complexity, what is it going to be? Well, let's go ahead and go back to this step. Because we enumerate all the subarrays, it is going to take order of n square time. That's because there are order of n square subarrays for an order of n size array. Alright, so we take order of n square to just generate all the subarrays in the first place. But then we have to go over all those subarrays and then figure out the minimums. So this is actually order of n on top of the order of n square, giving us order of n cube time and order of 1 space. Now this is already too much work, but is there a way we can optimize the solution? Let's go ahead and take a step back and look at what we are doing. Given the input, we had to enumerate all the subarrays and then find their minimums. But in cases like these where it seems like there is no other way out, this is what I always recommend. Go ahead and flip the problem on its own head. So now instead of going from the subarray to the minimum, I'm going to go from the minimum to the subarray. Okay, wait, what? Let me go ahead and explain, because this is going to be mind-blowingly awesome. Okay, let's go ahead and take a look at a single element like this, right? So at the index 2, we have the value 2. And what I'm going to do is I'm going to say, assuming this is the minimum, can you go ahead and find all of the subarrays it is the minimum element in? In other words, can you figure out the span of the elements for which all of the subarrays that will ever be generated to will be the minimum possible value? Okay, so what are we really trying to ask here? Well, since we want to figure out the places where 2 can be the minimum possible values of all the subarrays, we can see that the only real competitor 2 ever has is the value 1. So how about this? How about say that 2 expands to this region and says that 2 is going to be the minimum value of this entire region. Of all the subarrays inside of this region from the left to the right, 2 is going to be the minimum possible value. That's because we don't have 1 over here, because 1 is going to compete with 2 for the minimum position, right? So you can see that we have 3, 2, 4, 3. All of the values that are going to be greater than 2 are present in this section. Okay, so now let me go ahead and take a step back. From this input array, can we again go ahead and write down all of the subarrays where 2 is the minimum element in? So we have the single element 2, we have 3, 2, 2, 4, 3, 2, 4, 2, 4, 3, and 3, 2, 4, 3. What is the total number of elements we see? We see that 2 is the minimum element for 6 of these subarrays, right? This was the input given to us. And we figured out that this 2 is going to be present in 6 of these subarrays. So we can multiply them together and add them at the end for the resultant. Okay, but wait a second. If we have to enumerate all the subarrays to get the 6, well, there is no point of doing this kind of logic. Is there a better way we can figure out what this 6 really means? Okay, let's go ahead and take a step back. Right, we'll take a step back and let's say that we have a case like this, right? This is a completely different situation. Let's say that you're present on the left side of this maze. Now you have 2 doors, 2 yellow doors opening first, and then you have 3 green doors towards the end. And the goal of this is for you to move from the start to the end over here. So you can pick any of these 2 yellow doors, and then you can pick any of these 3 green doors to get to the end. Now let me ask you the question. What is the unique number of ways we can go from these yellow doors to the green doors? You can realize that if I pick the first yellow door, the yellow door on the top, I have 3 options available with me. Similarly, if I pick the bottom one, I have 3 more options that unlock. So in fact, we're looking at a total of 6 possible unique paths I can take to go from the left to the right. Right? So we can say that there are 2 yellow doors and there are 3 green doors. And just by using basic permutation combination, just simple logic, we can see that there are a total of 2 times 3 possibilities, 2 times 3 unique paths that I can take to go from the start to the end. Now, how does this tie into our example input? Here's the thing. For the elements to the left of this 2, including 2 itself, we can say that the subarray can start from any of these indices. And for elements to the right of this 2, including 2 itself, we can say that the subarray can end at any one of these 3 indices. In other words, I'm saying that the yellow doors are actually the indices 1 and 2, and the green doors are the indices 2, 3, and 4. And what we can see is the subarray, of which 2 is going to be the minimum element, the total number of subarrays is going to be defined like this. We are going to say that since there are 2 elements to the left of this 2, including itself, we can say that there are 2 doors that open like in the yellow case. And since there are 3 doors on the right hand side where this subarray can end, we can say that there are a total of 2 times 3 possible combinations. The subarray can start at any one of these 1 or 2 and can end at 2 or 3 or 4. Let me go ahead and actually take you back to this visualization. When we focused on the values where the 2 was minimum, we had cases like these. Let me go ahead and arrange this in a neat format. What do you see? We have 6 cases, yes, that we know, but look at the start and the ends. The starting values can be unique values of either 2 or 3, starting at the indices 1 or 2. And the ending positions are what? The ending positions are the values 2, 4, and 3 present at the indices 2, 3, and 4 respectively. What does this mean? This means that just by looking at a number, say in this case 2, and finding the left and the right spans of this number, again, if you are not familiar with the idea of spans, go back to the previous video on largest area rectangle in histogram. I've explained the idea of spans in much more detail. Anyways, for this current element 2, I'm going to figure out the left and the right spans. The area, the total area where 2 is going to dominate as the minimum possible value. And so by figuring out the left and the right spans, I'm going to take both of their lengths, which are 2 and 3 respectively, multiply them together, and we have the final answer as 2, which is the current value, times 2 times 3. All right. So what is going to be the space-time complexity now? Again, remember from largest rectangle area in a histogram, we realize that the space-time complexities are going to be order of n squared in terms of time and order of 1 in terms of space. So look at what we have done. Just by reversing the problem, flipping the problem on its own head, and instead of going from subarray to the minimum, if we go from minimum to the subarray, that is, we ask the question for this current element, assuming this is the minimum possible value, what is the number of subarrays it is going to be present in? And because we are doing this kind of computation, because we are trying to find the span of this current element, and we'll do this for every single one, we can say that the time complexity is order of n squared. All right. Again, what am I doing? I'll iterate over every single element one by one for each of them. I'll ask the question, what are the left and the right spans? And we can find that by iterating again to the left and the right. We basically want to find the entire range of areas where 2 dominates as the minimum possible value. Okay, now it should start making a lot more sense. But at this point, I want to pause. We converted an order of n cube solution to an order of n squared solution. But is there a way we can make this better? Is there a way we can bring down the time even more? Let's go ahead and talk about the optimized solution. All right, so let's go ahead and take a case like this. For any current element I, what is the area, what is the span of area it is going to dominate? Well, it is going to dominate all of the area. It is going to dominate all of the area till it finds an L and an R on the left and the right side respectively. That is, L is the first left value from I that is going to be lower than I, which means that I cannot dominate the area governed by L, right? And similarly for R, as soon as we get a value R, we have to take a step back. We can say that, you know what, R is a value lower than me, which means that it is going to dominate another sort of area which I don't want to go into. So left and right, L and R are going to bound my area of domination, right? So now how can we implement this? In fact, what we have to use is a monotonically increasing stack, just like in the previous case, right? Just like in the previous question we saw, we have to use a monotonically increasing stack. The reason remains the exact same. So now that we have this kind of structure, let's go ahead and simulate what is going to happen. Let's say that we get a rectangle like this. Let's say we get a value like this. Now this is obviously lower than the current value which is present on the top of the stack. What does that mean? That means that for the value on the top of the stack, we have actually found a right value which is going to bound it, right? Can we say that? For this current value, we have found a right value which is going to bound it. But what about the left value? Since we have a monotonically increasing stack, by the nature of the stack itself, we can say that just look at the left of the stack top and you will be able to find a lesser value. This is by default because we have used a monotonically increasing stack. And this way we have found the left and the right bounding indices for any given element, right? So we have found the answer for this guy. Okay, so how do we go about now implementing this? The first thing we do is the first change we make is call this current guy R, which is going to be the rightmost bounding area, right? R is going to define the maximum area to the right this current green rectangle can span. All right. So the next step, as we did earlier, was we are going to pop this element out of the stack. We are going to say I is the current value I'm going to focus on, and I've already found the R. Now what is the L going to be? The L is now going to be the top of the stack. Okay, cool. So now this should refresh your memory. This should make a lot more sense what we are doing. Again, just like in the previous case, we're going to say that L is equal to the stack top only and only if the stack exists. Otherwise, we have to assign it the default value of -1, saying that it exists somewhere to the left of this y-axis. Okay, cool. So now let's go ahead and clean this up once again. And let's go ahead and write some more code in this space. Again, what do we have to do? We have to figure out the right span and the left span. The right span is going to be R minus I, and the left span is going to be I minus L. Remember in the previous solution, we saw that it was actually R minus I minus 1, and the left span was I minus L minus 1. In this case, however, we remove these minus 1s, because we have to include the current element itself. Okay, cool. So now that we have the left span and the right span, what is the number of subarrays this current element I is the minimum in? The count of these subarrays is going to be left span times the right span. And now what is going to be the answer? Since the answer was to find the sum of all of these minimum values of each of these subarrays, we can say that answer plus equals to the current element times the count. That is, we have found the minimum element A of I, and we have figured out in which all number of arrays, the count number of subarrays, A of I is going to be the minimum element in. This leads us to the space and time complexity of order of n each. All right, let's go ahead and implement this bad boy. Okay, so the first thing I want to do is set up the stack, which is going to be an empty stack monotonically increasing. So we'll write mono inc. Okay, now I want to iterate for I in the range of n, where n is the length of the array. By the way, I'm going to change this array to a. Okay, cool. Now what do? I want to append this I to the stack. But before I do that, I have to also check the while condition. So while the stack exists and the A of I is following some condition with the A of stack top, then we have to do something. All right. What is the condition going to be? This is a monotonically increasing stack, which means that we'll have a smiley. Okay. So this is a happy guy. Cool. What are we going to do now? We want to pop the element I out of the stack. And we're going to find the answer for this current I. That is, I want to do answer plus equals to A of I times the count. Now what is the count? The count is going to be the left span times the right span. Okay, what are the left and the right spans going to be? Left span is what? I minus L. And the right span is R minus I. Again, all of this is something we've already seen before. Now what is L? L is going to be the stack top if stack exists, else minus 1. Oh, by the way, a quick check that we have to do. This is not actually A of I, this is A of R. And we'll also change it over here. Okay, cool. So now this should make a lot more sense. And we can return the answer at the end. Let's also initialize the answer over here to 0. Okay, let's go ahead and run it on a sample test case. And wait a second. This is the wrong answer. Why is that? We followed the logic perfectly, right? But just like in the previous case, we have to do one more check. We have to do a.append minus infinity. And that is so that we can ensure that the monotonically increasing stack is always resolved at the end. Say, for example, we have a case like 1, 2, 3, 4, 5. In this kind of case, we will never be able to find a right side position which is able to kick out all of these elements. So we'll have to do .append a very low value so that it is able to kick out all of these elements one by one. If this does not make sense, go ahead and check back the previous video once again, because that is going to clear a lot of things up. Okay, anyways, let's go ahead and clear this out and we'll try the running the code once again. Cool, so this gets accepted. One more implementation level detail is that since the answer may be large, we have to return the answer modulo 10 to the power 9 plus 7. So let's go ahead and create that one. So we have 10 to the power 9 plus 7, and we'll simply do answer mod. This, by the way, is not a good way to do it if you are especially in other languages like C++ and Java. So we'll also do this just for the sake of clarity. We'll mod every single thing, even the answer. Okay, cool. I'm finally feeling confident enough to run this code, and let's go ahead and submit this. All right, cool. We get it accepted. And so this is it for the solution to the problem, sum of subarray minimums. All right, so this is it for the course on stacks. We looked at 15 different popular interview questions, and we slowly built up our intuitions from the easier ones all the way to the harder ones. Great job on completing this entire course, and I'm going to create many more courses along the way, so stay tuned for that. Anyways, this is it for this course, and as always, thank you for watching.